और जाएगा ठीक है, तो ठीक यहीं पे है ना, नीचे आएगा ठीक है। हाँ Yeah, good morning to all. We are in this third day of our GIAN course, that is on combustion theory and applications. In the first 2 days, I had given the concept of thermodynamics. Then we tried to bring the thermodynamic concept into combustions. Then we also studied some fundamental concepts of combustions and chemical kinetics as well. Then we tried to merge fundamental equation of thermodynamics with the chemical kinetics. When we merge them, we try to frame a set of equations that are that can be modeled analytically with mathematical forms such as mass conservation, species conservation, momentum and energy. All these equations can be derived. Additionally, we also emphasized about reactors, in which we can link the closed and open system concept of thermodynamics through this reactor, so that equations can be effectively modeled. Then we also give some fundamental concepts of combustions such as adiabatic flame temperature, equilibrium products of combustion, then we introduce heating value of fuel, all sorts of things, and of course equilibrium constants, rate coefficients. All those parameters are basic requirement for the combustion studies. Now moving further, in this lecture which is entitled as thermodynamics of reactive systems, we will move further, and it is part 2. We will try to see that although we have given a coupling systems in which the reaction kinetics of combustions can be linked to the concepts of closed system, open system equations involving first law and second law. But then how to frame that equations for a reactive systems, and in fact conservation methods of reacting flow helps us to frame the analytical modeling, and in fact most of the combustion modelings, whatever software you use, we try to see we try to evolve that these equations needs to be solved. 3 fundamental equations: mass, energy and momentum. These are typically used in the fluid mechanics concept. Thermodynamically, we say that first law, second law analysis has to be satisfied. Third, bring combustion into pictures. Now when you combine 3 things together, fluid mechanics governing equations, mass, momentum, energy, and this thermodynamics equations like first law, second law, and entropy equations. Both the things we integrate with chemical kinetics and reactions, chemical kinetics of reactions. Then when you couple them, we frame the combustion equations, and here we call this as a conservation methods, that means framing the reactions. And here I need to emphasize that as far as fluid mechanics is concerned, we are really bothered about mostly on momentum equations, but you will find that momentum equations is not that significant when you do combustion, because it's instantaneous events, and there is no velocity component involved in this picture, as long as we are going for high speed combustion. Then we will try to introduce this multi-component diffusion. In our last concept, we talked about Fick's law of diffusion, which tried to evolve that how two species combines each other, and based on this we find the flux equations in and specifically for species flux. Here multi-component diffusion is another concept which evolves, as that in a combustion environment it is not only two species that combine. There are possibilities, because if you see this room as if it is a reactor, and fuel and air is initially there and combustion has happened, we ignite. So, we will find n number of species that comes out from these reactions. I have already mentioned that there are global reactions, there are elementary reactions. Possibility of elementary reactions are based on the fuel and air constituent species, and the reaction can happen at atomic level, molecular level. It can also happen if temperature is so high, it can happen in ionized level. And in this process, since it is a closed environment, or reactor is a closed environment, we can see that there are possibilities that sometimes, depending on the initiation of reactions, some zones are too hot, some zones are too light. This is typically what you do in diesel engines when fuel is injected. So, in some zones reaction the phi, which is equivalence ratio, is lean, rich. So, we cannot predict the temperatures to be uniform throughout that reactor or throughout that domain. So, for that reason different species are formed. They try to combine among themselves depending on pressure, temperature conditions in that domain. So, when they combine, the concept of Fick's law drops in, where we have to include that concept of diffusion coefficients. One species tries to diffuse with other to make a recombination. So, this comes under this multi-component diffusion, because there is no two species, there may be n number of species, and possibility of combination can be many. Another important term, we call this as a conserved scalar. This conserved scalar is another concept which is introduced mainly to tackle these conservation equations. What is that conserved scalar? It is a generic term. So, previously I told you about this equivalence ratio phi, and this equivalence ratio phi changes from depending on the flammability limit and combustions to happen. It changes from 0.8 to 1.2 in a typical engine environment. But what happens that as far as when you say the fuel air mixture is already pre-mixed, the role of equivalence ratio makes some sense. Okay? And when it is a non pre-mixed, means air comes separately, fuel comes separately. So, means equivalence ratio changes in this combustion domain. It cannot be it changes drastically. So, some zones the fuel is completely rich, some zone fuel is completely lean, because they are not mixed properly as per the stoichiometric conditions. So, such cases, what is the criteria that fuel remains its identity? Fuel remains its mainly fuel when it is pre-mixed, fuel remains its identity through the value of equivalence ratio. We say it is lean or rich. But lean rich means we know at least the percentage of fuel and air combination. But in an environment where it is a non-premixed, the role of phi does not seem to be appropriate. So, for that reasons we try to find out another parameter. We have to find out another parameter apart from phi, through which we can keep the fuel identity or one parameter to be conserved everywhere in the flow field or in the domain. So, that term equivalence ratio is one kind of conserved scalar, but it is not true for all kinds of situations, pre-mixed or non-premixed. So, that way we define a term conserved scalar for an which has to be taken into account through these conservation equations. In other words, we try to mean that conserved scalar parameter is linked to equivalence ratio phi, but reverse we are not going to do. That is what the mathematical representation talks about. Then already I told you about equilibrium products of combustion. So, through these products of combustion we try to see various species are formed, NO, CO, NO2, CO2, all species irrespective whether the mixture is rich or lean. And when these species are formed, that is the reality, and in our chemical kinetics term we say these species are going to be formed whether mixture is rich or lean. I had given you some standard equations in which we do this, we find the stoichiometric coefficients by balancing the atoms. But in terms of chemistry point of view, we want to see that because if you look at that curve, you will find the NO formations comes in both lean as well as rich. CO formation is also formed in the lean and rich. But is there any mechanism in which we can say NO formation in lean region is because of this region, NO formation of CO and NO in rich region is because of certain regions. So, through these things we will try to evolve the typical formation of compounds like CO, NOx, why it is formed, and if it is formed, whether it is due to temperature, due to pressure or equivalence ratio or for any other reasons. What is that mechanism, why it is formed? If you say it is because of temperature, then why, if you say that normally in our Arrhenius equations we say reaction is mainly governed by the temperatures control, because it is a main function of temperature. If at high temperature NO or CO is formed, why it is forming in low temperatures? Because our curves indicate that. So, those things we try to find out what is the mechanism of reactions. Now, apart from this, one important as a case study, I will try to emphasize a hydrogen oxygen reaction system, which is hydrogen is a very good fuel, oxygen is a oxidizer. So, when you want to have these combinations, what are as a case study I will try to explain that what are the possible elementary reactions are formed, and through these reactions how we can say whether of course, in this combination you will not have CO NO formation, but it will talk about what are the cause of these reactions, and this will emphasize whether it is a very good practical case where you need to demonstrate the chain reactions, chain initiation reactions, then chain reactions, chain termination reaction, all reactions can be a model. So, this is the overview of what I am going to discuss here. So, to start with, this is conservation of methods for reacting flows. So, there are three ways one can model. One is steady one dimensional planar geometry in which x coordinate is only there. Second one is steady one dimensional spherical geometry where r coordinates with radial coordinates, and third is two dimensional axisymmetry. So, typically this is schematically one can show like this. Now, what are these connection with our combustion modeling? So, for example, when you have planar flame, it is like a plane, the flame like in SI engines, a flame is initiated and tries to propagate in the domain. So, that is a planar flame which moves in that domain. Now, if you why it is a spherical domain, why it is necessary? Because in a diesel engines we inject the fuel through injectors. Fuel comes as a small droplets, liquid droplets initially, and with high environment the droplets evaporates. Means it is like a fuel is can be assumed to be initially at certain diameter, and when it evaporates it vanishes. Means its initial radius, if a droplet you can design at its initial radius with r0, that vanishes when it evaporates. So, that way this modeling we can say it is a spherical flame. Of course, that is at fuel level. Now, there is another way we can think about this axisymmetric jet. This fuel, when it is injected, it is with certain pressure. Normally, this we call it as fuel injection pressure, and it comes as a jet. When it is jets, it has certain momentum, initial momentum, and when it enters to the combustion domain, because of its initial momentum, the jet, it creates a free jet within the domain, and this when it comes, at least if you say assume that this is a kind of a diameter of fuel nozzle, it comes a jet, and this jet has some free boundary, and with this momentum it can go with a maximum axial distance, and across this we will have, because along its axis the strength of fuel is very high, which is rich, and when you go outside it becomes linear. So, this is how we say fuel comes as a jet. So, that is the reason these are the three kind of situations normally or classically we call this as a analysis of conservation methods. So, first type of things when you talk about conservation equation, which is mass. In fluid mechanics term, CFDs we usually focus on mass, because the initial the gas does not break into species. When it species, then it becomes we will have two equations, not only mass conservation, you will also have to species conservation equation that you have to frame based on the Fick's law. And there are two types of velocities through this we can happen, one can define. One is the bulk velocity, other is the diffusional velocity. The fluid velocity is referred as a mass average bulk velocity. That means you take entire mass involving this as a bulk velocity, and difference between the species velocity and bulk velocity is diffusional velocity, which means that when after the combustion is done, species are formed, they have their own velocity, and when you take difference between the, because they travel much faster, and difference between species velocity and bulk velocity is the diffusional velocity. So, talking into this and multiplying it by its mole fraction factor, we get the species conservation equations. So, this is how we frame this equation, overall mass conservation equations here. And when you say species conservation equation, this rho stands as a global density of the mixture. Now, when species equation comes, we take this equation is reframed with respect to that species based on its mole fraction. And here this total velocity is the combination of this. So, through this we get two equations needs to be solved, overall mass conservation and species conservation. This is again a continuation of same mass and species conservation. Through this we can get two main equations, mass conservation equations and species conservation equations. To address these species conservation equations, we have to take the help of the Fick's law for a binary mixture. If it is a two species binary mixtures, and we can frame for each species what species equation M A and M B. The next thing, this is how a mass conservation equation is evolved for in a domain that which is 3 types, planar or axisymmetric or spherical coordinates. Then for that also again moving further, we also look at momentum conservations, and this momentum conservation has not direct relevance to this combustion domain. Sometimes people ignore these momentum equations while simulating combustion flow, but energy equations is very vital, that involves very complicated one dimensional equation like this, and there are many models that were evolved. One simple model that involves is the Zeldovich energy equations, that takes care about the variation of in the this enthalpy, which is a function of Cp and T, and Cp also changes during this process, because Cp normally Cp value remains, can be taken to be a constant value within, if it is a 1000 degree, but more than that accuracy drops down. So, it has to be both Cp as well as temperature effect has to be included. Then here another term that drops in here, where we call this as a binary which is a diffusion coefficient, and right hand side equation, whatever initial energy it has, final energy is based on the enthalpies of that species with its species flux. So, for each species we need to find one term. For each fuel and air mixture you have to find one term. So, it is a written in summation form. So, it is a very complicated equations. Typically those equations are addressed for each chemical reactions to frame the complete combustion modeling equation. Additionally, when you look at this, when you frame these equations, you also have to look into the diffusion effects during this combustion process. So, Fick's law introduces binary diffusion. Now, this binary diffusion normally does not give sufficient information. So, we enter into a concept called multi-component diffusion. And this multi-component diffusion has tremendous effects, which means that the effect of pressure and temperature simultaneously in the combustion domain. Sometimes we will have sometimes one reaction is dominant when the pressure dominant with respect to pressure. Some reactions were dominant with respect to low temperatures. Some reactions are dominant with high temperature, which means that reaction type which are formed at low temperature do not show their effect at high temperature, and other way around. So, so that way it is a very complicated phenomena. We really do not know. We can really did not standardize it with respect to specific fuel. Maybe one end we can say for hydrocarbon fuels, these are the possible reactions. For other types of, because mostly hydrocarbon fuels can be of two types. One is there are chemical structure talks about alkyne, alkaline. There are three structures of organic compounds. So that way the equations needs to be resolved for each kind of fuel air combinations. So to address those large temperature effects, there is a term called as Soret effect, which is used when we have large temperatures, and there are some situations when you have thermal diffusions, in which light molecules tries to diffuse from low temperature to high temperature regions, heavy molecules try to come from high to low temperature regions. So these are the quantitative statements that need to be accounted to frame these are qualitative statements that needs to be accounted for to frame the quantitative equations. So what is that multi-component diffusions? So by looking at all kinds of fuel studies, the multi-component diffusions falls in the four category. First is ordinary diffusion. So Fick's law only talks about ordinary diffusion, which is mainly due to concentration gradient. One end, that perfume has concentration of perfume is high at one end of the room, but when it spreads, its concentration drops down. So this is the ordinary diffusion which can be addressed by Fick's law. Thermal or thermal diffusion. The word thermal diffusion is common term, generic term, but specifically we call this as a Soret diffusion, because he only framed the effect of those diffusions resulting from combustion, which is mainly due to temperature gradients. So when there is a large temperature gradients, so that Soret diffusion equation is to be taken into account. And typically this is in normal reaction cases, this is a standard case, and in which we have seen that Arrhenius equation, which is a function of temperature. So since it is a function of temperature, so when you say that temperature effect is more predominant than pressure, then we can simply do our analysis or modeling can stop at this point. But then side by side, when you say in a reaction, if the temperature as well as pressure is more significant, because normally when a high speed flows, formation of shock wave is there. The shock wave creates sudden gradient in the pressure as well as temperatures. So pressure effect has to be included. So that way we cannot neglect the effect of pressures. So that has to be included here. Then forced diffusion, which is resulting from unequal body forces. So forced diffusion, we look at a sense that if you look globally at atomic level, if you look at the reactions only at molecular level or atomic level, and try to see when both pressure and temperature effect are so high, we really do not bother whether it is in atomic stage or still it is further it is in ionic stage or plasma state. So when you say plasma, it is a hot plasma, you do not know, and the role of atoms has no effect. So in one end we have some kind of hot plasma, other domain we don't have so let us say other domain we still we are in atomic level. So it assumes that this hot plasma acts as a kind of a separate body force that drives the reaction. So it say both pressure and temperature effects when included, that results in the force diffusion equation. That is the reason says that it is unequal forces among species. Forces comes from Newton's law, but it is a inertia based situation. But when you say body forces, that comes among species, species size in the micron level, and if those effects has to be there, then we need to take into account the molecular weight of that atom has no bearing. So, that is the reason this unequal body force comes. So, what we see here, that if you go from top to from ordinary to forced, the complexity of modeling keeps on increasing. So, really you do not have to go for this unless and until pressure and effects are there. So, we can stop the standard. If it is simple flame which is burning, we can stop something at this level or this level or this level. So, complexity of combustion equation increases. So, this is about how the philosophical or viewpoint of the equations. Now, coming back to the some mathematical treatment. So, we now have to introduce the terms like diffusion mass flux, diffusion velocities, and since this is represented in terms of so what you see in this equation is two things. One is we need to look into the global picture, and we call this as a mixture, which is let us say molecular weight of the mixture, and with respect to species we also have to find their respective molecular weight. That is the reason I told no mass conservation equation does not come here. We have to, and this analysis has to be done on molar basis. Remember, this is on molar basis, because this equation has R bar. R is characteristic gas constant, this R bar is universal gas constant, which is true for all kinds of species as well. So, all this analysis has to be done in molar basis or molar concentration equation, and here the terms like yi and xi, they are treated as a mole fraction. Okay, this is what we call as a diffusion flux, which is mainly due to concentration effect, which is mainly ordinary diffusion term. And here when you use Dij, we call this as a binary, as a diffusion coefficient, which is with respect to ordinary diffusion. Now, when you come back these flux velocities, diffusion flux velocities for species, which is mainly for with respect to temperatures, this equation terms as here it is in a vectorial form. We have temperature gradient, this with respect to this temperature gradient, and that is what we call as Soret equations. It has two terms like its mole fraction, global density, and D. D stands as diffusion coefficient, and there is a term superscript T, which means this diffusion velocity is due to temperature. So, these equations are simple, but the way it has been written, it makes it complicated, because we need to address all these points. And again moving further, this is a combination of all types of equations, and what most important thing that I need to emphasize here, here diffusion velocity due to concentration is given by this. So, this has to be taken into account. Now, for binary, then you have the term like binary diffusion coefficients for species species fluxes or diffusion fluxes. Now, moving further, I have told that a parameter which has to be defined in a combustion framework, typically it is called as a conserved scalar. By definition, it goes like this: a conserved scalar is any scalar property that remains conserved throughout the flow. Okay. When we say it is a pre-mixed case, obviously we say that the charge is fuel and air concentration remains same. When it is a non-pre-mixed, phi does not give same bearing. So, you have to bring another parameter which keeps the fuel identity to be constant throughout this domain. So, these explanations we have given: mass fractions, absolute enthalpy, which is typically another kind of a conserved scalar parameters. For with respect to fuel point of view, we will try to define another parameter apart from this equivalence ratio. And here that extra parameter we call this as a mixture mass fraction. So, this mixture mass fraction is defined as a conserved scalar, which is the ratio of mass of the material having origin from fuel stream, having origin, this needs to be emphasized, origin from fuel stream to the mass of the mixture. Normally when you say phi, it is either mf by ma or ma by mf, but this mixture fraction is represented in a different way. First thing is that one is mass of the mixture, that is by definition how do you quantify? The mass of the mixture is m mixture. Mass of the material that originates from fuel stream, and in the for hydrocarbon fuel it is in the carbon and hydrogen. So, you take that entity separately, instead of fuel as a whole its molecular weight, you take them their identity separately. Okay. So, because these sometimes what happens, this mass will be higher or sometimes carbon mass will be higher, because we do not have same equivalence ratio throughout the flow field. So, that way the mixture fraction keeps varying, but mixture fraction may be same, but these masses may vary. Mixture fraction has to be same, but this is varying. So, we can model this same mixture fraction everywhere by regulating two terms at a time, MC or MH. So, this boils down to a term that when we have a 1 kg of fuel, some mu kg of oxidizer, we get mu plus 1 kg of products. So, for that, if you say try to find the mixture fraction, we say for fuel, which is YF, for fuel it is this carbon and hydrogen becomes 1, for products it is 1 by mu plus 1, because here it is here, and for oxidizer this value is 0. For oxidizer there is no carbon, so this number is 0. For fuel, that is because if this is reactant, this is products. So, complete way, if you find out the mixture fraction of this reaction, we can have this number. So, this boils down to a function of YF, which is kg of fuel per mixture, Y product kg of products per kg of mixture. So, that way we can find out the mixture fraction for that system. So, this is the case where for a 3 species systems. If you have multiple species involving catalyst and others, this number has to be found out, considering the fact in that catalyst whether there is a identity of carbon or hydrogen or not. So, these things I have emphasized in the previous lectures, in which I talked about this equilibrium products of combustions involving for a standard hydrocarbon fuels, and we also talked about unimolecular, bimolecular, termomolecular reactions. We have water gas shift equilibrium and rate equations. So, having said this, we talked about these two curves, two major curves. One is because we have phi is your equivalence ratio with respect to this phi, the we plot the terms in terms of mole fraction, temperature, equivalence ratio, just to give the things that when we have the major products that comes out when during a lean combustion. Lean combustion it is means which is more in air. We see in this case we can say maximum heat release that comes with equivalence ratio 5 is 1.05, and through this process when the reaction starts, normally highest temperature the highest temperature is not exactly at 1, it is typically at 1.05, for which maximum temperature is 2278 Kelvin. This is the first curve that we say this is the upper limit of this reaction system during a lean combustion. But what happens now, since we have a flammability limit during an ice engine combustion is 0.8 to 1.2, we see here that how with the one product, that water concentration mole fraction changes with equivalence ratio, and how the CO2 things changes with equivalence ratio. If you see here, nitrogen normally during this region has no effect, and when we have oxygen concentration drops, CO concentration keeps on increasing because it has to give you CO2. So, initially CO concentration increases, when it increases O2 concentration drops, these two things give CO2, and one point of time the CO and CO2 after that CO2 concentration drops, one point of time they meet at a point. So, this is what you see globally, but when you have globally for a lean combustions, but when you have rich combustions, so in that case we expect the fuel terms are fuel components are higher, so it is a rich combustion. You will find products like which is not seen here, because all these products are radicals like NO, OH, CO, we have simply O term, and with various equivalence ratio their concentrations, there are some concentration keeps on increasing, some are increasing and decreasing. So, for example, if this is the case CO, so it starts from this and it goes up to this, and O2 concentration obviously drops when it becomes richer. Hydrogen concentration one point of time increases, then comes down. So, why I am trying to say is that what is the mechanism, because here also we see there are CO formation, here also we see CO formation here. A very basic difference between these two, we see the CO formation only at higher equivalence ratio, but here if you see, so here we see CO formation, it is at low equivalence ratio. And what is the cause of CO formation at this case? What is the cause of CO formation? Because these two things are contradicting. So, that is what we are trying to say. What if to find out cause of CO? This is one particular case study I am saying. Similarly, for NO as well, we do not see NO here, rather you see everywhere we have NO concentration is increasing in this beginning, and towards the later part it drops. Okay. So, why these effects are coming into picture? What is the mechanism? So, those reasons we need to find out what is called as mechanism of CO formation or NO formation. So, this part I will talk later. Here I want to try to emphasize that why what is the reason for carbon monoxide oxidant, why the CO formation happens. So, if you bring the chemistry into it, while bringing the chemistry into it, we bring elementary reactions into picture. So, there are two ways the CO formation can be done, that was the chemistry talks about. through this when there is sees water. Now, if it is there are possible elementary reactions that can happen, CO can react with O2 to give CO2, because that is the thing that it has to and the reaction should stop at this point. CO2 when it forms, it has to happen, and it can give AO. So, this is how the chain when chain, this is what we call as chain initiation sequence. It starts, then when there is a O, it left out O, it tries to see with H2O, it can form these two. This is called as hydroxyl radical formation. Now, again in that domain CO is there, it sees OH, it tries to form CO2. This is the called main key oxidation reactions. So, and then to propagate this chain to form this CO2 completely, this hydrogen and oxygen can react to form this OH. When there is OH, again it tries to see CO. So, it will try to form this. So, this is a mainly key oxidation reaction, that is what we are supposed to have it. Now, in this process, if we see CO and O2 try to find out CO2 and O, its process is slow. When we see, when some reaction, if you can some way make OH, and so that it can take CO to form CO2. So, that process is much faster. So, it is a basically fast reaction. So, normally when you try to reduce the pollutant levels, we try to initiate some kind of branch or chain reaction such a way that we make these reactions to be faster. And at the end of the day, we have to kill this CO to bring down to bring it to CO2. So, this is the concept how we can get CO2 from CO. When CO, another mechanism, it is is CO through hydrogen. When you try to bring through hydrogen, if you try to link up, this is something called as H2O2 systems. So, some way we have to find this kind of, these radicals, hydroxyl radicals, and that radicals keeps on propagating. Ultimately, at the end of these things, we will land up CO2. This is another mechanism, CO can bring to CO2. So, while why these equations are important, because these are elementary equations. So, in a combustion domain, that is complete hydrocarbon fuels, you have to create some kind of, some environment has been created or due to its reaction, or you have to initiate some forcibly in this domain to bring completely this CO2, we have to bring it to CO2 come to CO2. Okay. So, this is what the mechanism of carbon monoxide formation. Now, coming back to nitrogen formation, oxidation of oxides of nitrogen formation, NO formation. So, NO formation has some effects. It may be due to two important factors. One is due to equivalence ratio, other is due to its temperature. And in fact, this is main culprits for air pollutions, because nobody wants this. And NO formation can happen in these routes. There are three mechanisms. One is very standard mechanism, which is called thermal mechanism or Zeldovich mechanism, which talks about, which mainly takes Arrhenius equations, and he framed through that binary multi-component diffusion equations, we get these mechanisms. And when you see Arrhenius equations, normally when the environment is 1800 degree and above, this mechanism is realized. We do not feel thermal effect below this. That means, it is improper to use these concepts, Geldovi's concept, when you do not talk about temperature above 1800 Kelvin. So, it is more or less this is true for all kinds of steady reactions when the temperature is happening above this. Another kind of situation which is a short duration time scale, millisecond, microsecond time scale, it is a prompt a mechanism that during that time also we can have NO formation. That is the reason when you simply ignite initially for short time you may see nitrogen, after that it vanishes, because dominance of Geldovi's mechanism comes into picture due to because initially temperature rises first, NO started forming, but it suddenly sees high temperature. So, this mechanism dominates. So, it is a that is the reason when you are looking at that reaction in a very short time scale, this is true, and because of this reason we see that for rich mixtures we find NO. And N2O is another intermediate mechanism which normally says that N2O really does not have an identity, either it is NO or NO2, and that, but however N2O is a compound that is merely seen at low temperatures, equivalent lean mixtures. So, these thumb rules or rules has to be included whenever we look at a chemical reactions, that is in a broader domain with respect to your equivalence ratio and temperature. And since at this stage we are not looking at the pressure effects, because they are in a different domain, shock wave formation and above. So, as a rule of thumb, thermal mechanism is usually irrelevant for temperature below 1018 Kelvin. And with respect to time scale of oxygen formation, NO is formed rather slowly in thermal mechanism. NO is generally formed in the post flame gases. So, these are the inferences that we get out of it. And here I have mentioned why why there is a distinction of different combustion products which is seen in reality for hydrocarbon fuels, and all those mechanisms gives answers to these curves. Now, what is that Geldovi's mechanism? It here if you take that reaction in a mathematical form, this how it says how this NO formation happens with nitrogen at these things. So, they use the rate equations and find and as if it is a reversible reactions, one can look at the reactions effectively when it moves in a forward direction and when it moves a reverse directions. They would have different value of rate coefficients, and they uses this Arrhenius equations, that is, and this number stands as activation energy for that reaction. And finally, we say it is a function of temperature only. If you really want to find out the concentration of your NO at any point of time, the final equation boils down to this, and this OH and N are concentration of at any of that situation. And why this Fenimore or prompt mechanism? This talks about during this mechanism what happens. So, this is true for when it is for a short time scale and rich mixtures phi up to 1.2. So, before thermal mechanism dominates, NO is formed promptly through CH radicals. Why it is so? Because during initial reaction you may have CH. So, when there is N2 and it sees CH and it initiates the chain reaction, it gives HCN plus N, and then there is a chain sequence reaction. When it sees O, it gives NCO plus H, and all those reactions are reversible. One can you can shift its reaction. Then we have chain sequence reactions, and NO is formed. Now, when this keeps on happening up to when this Geldovis mechanism dominates, that means in the domain when temperature rises, these effects are nullified. Okay, this is how what happens during that reaction domain. And there is another point at which is a mainly for use N2O as intermediate mechanisms. So, in N2O mechanism, what we have is this it is important when when we have a fuel lean mixture. When you have a fuel lean mixture, it is typically a low temperature conditions, and it is normally do not seen in IC engine environment. It is seen in the gas turbine environment. So, this is also similar to NO effect as we see in our previous case. And there are some possibilities that when we are using solid fuels like wood burning, there is a possibility that we can have NO formations. So, solid fuel NO formation are governed by this. This is initiated through this N2O intermediate mechanisms. So, O and N2, this gives N2O. N2O, when it sees hydrogen from this fuel, we say it gives NO, and in the chemical form they have standardized a particular route in which we start from fuel which is a hydrocarbon fuel, and when it gets or experienced with nitrogen from air, these are the possible routes for formation of various atoms and radicals, and ultimately they land off whatever nitrogen we have, it comes as it is, and this also adds to NO here. And this NO also can be killed if you can take them back to this route. So, as long as the fuel concentration is reduces, so we keep formulating through this cycle, so that NO formulation is reduced and N2 concentration which is already there, it improves. So, that way we can effectively manage through these chemical processes by reducing the oxides of nitrogen. This is again here point that needs to be emphasized here, that we have NO2 formation, and from NO there is a possibility we can get NO2, and NO2 again can recombine with hydrogen to give NO plus OH. So, whatever here I have shown here, OH, NH, all these things are the consequences of this. So, what our main requirement is that at high temperature NO2 formation is quite significant. Destruction of this NO2 reaction has become a necessity, and so we need to initiate some kind of catalytic events or mechanisms, or evolve some mechanism through which we can bring down the NO2 level from the atmosphere. Okay. And last slide, I just want to say that whatever I have shown that is mainly pretending to a case where we commonly encounter typical emission parameters through different chemical reactions involving involving mainly branch reactions, chain reactions and elementary reactions. And the concept remains true for all kinds of fuels involving this chemical structure, alkynyl fuels. So, whenever we have these two terms, hydrogen has a good effect with oxygen because it goes as water, but carbon does not have. But because of this carbon, temperature shoots up. When the temperature shoots up, air starts dissociated, so nitrogen effects dominates. Nitrogen it dominates, it gives NO2. So, because it is a consequence of one event with other, so basically people are looking at how we can reduce carbon from the fossil fuel. But however, over the statistics so far, hydrocarbons fuels are being used and complete process starts with methane to any kind of combination of these carbon fuels, and the reaction chemistry for fossil fuels are more or less same. So, whatever concept we have introduced, that is also true for any kind of fossil fuels. So, for today I will conclude, and these are the some sample problems that demonstrates how one can find out diffusion coefficients based on this kind of equations we have encountered here, and this is very vital, and this is nothing but your Soret diffusion. Okay. Then we have equations involving diffusional velocity for a multi-component systems. You can see for only for 3 systems the equations becomes this. If we can n number, and it is analytically possible. When you have n number of equations, you really cannot find out on its own. So, programming or matrix form of equation is required, and this is an demonstration that gives the mixture fraction calculations. So, in this mixture fraction calculation, which says that for this fuel you have to find out the carbon and hydrogen identity and write that main expression of mixture fraction for each of the constituents. And this mixture fraction calculation will tell you what is the value that remains its identity for all kinds of during the combustion process. So, with this I will conclude. Thank you for your attention. Okay, that is all, sir.
Short break or
Yeah.
please continue.
Yeah. Let you 1 hour, just 1 hour. We will take a break.
Until
15 minutes. 15 minutes.
we will start at half past.
What time?
Okay, so I will start. So we have discussed now a lot of theory, and it's sometimes difficult to understand all the theory without any proper application. So therefore we have decided, Professor Sahoo and me, to have here's 2 lectures about numerical simulation for combustion model using Cantera. So a lot of the details, especially concerning numerical modeling, will be explained in lectures which will be held maybe on Friday or next week. So some of the fundamentals may still be missing, but the advantages of Cantera is that if you want, you can install it on the fly today and start with some practical simulations, play with the details here, which hopefully helps you to understand all the fundamentals we have explained until now and which will come in further lectures. So I've started to study combustion in 1995. In my master's thesis I simulated the laser-induced fluorescence of OH radicals in a flame, and then with my PhD thesis I started to simulate ignition processes and flammability limits using 0D and 1D models, incorporating detailed chemistry. Why is this so important? So nowadays we are talking about exascale computing, so the computational quantities are getting better and better, and we can try we can simulate complete gas turbines in our computers today, but this of course is still very expensive concerning computational costs, and if you want to learn something most often 0D and 1D calculation are still the best tools, because within seconds, maybe minutes, you can vary a lot of parameters, and you can examine the influence of, for example, changing the hydrogen content in your mixture. Does it increase the flame velocity? Does it increase the pollution formation? It's not working. Okay.
It's on.
So now it's working?
Yeah. Nice.
Thank you. So within very short time you can examine a lot of parameters, and therefore it's a very valuable tool. So I have done this, as I said in my PhD thesis, with an in-house code written by my supervisor in Fortran. I'm still using this program because I know a lot of details, and if I want to change the code, I know how to handle this. But there exists a lot of in-house codes for these kind of simulations, and there are also existing packages like Chemkin, which is very popular because a lot of the mechanisms you can find in the literature are given in a Chemkin format. But I think a very popular open source solution we can use in our days is Cantera. It has excellent examples, and so the most complex thing using Cantera for me is the installation. Until it runs, until all libraries are included. So I'm sitting behind a firewall after I get access to all the things I need. That takes a lot of time, but when it is running, it's a very stable and very comfortable solution. Therefore, I want to present it here because, as I said, after this lecture, you can go home and install it directly and play with it. So it's an open source tool that can be used either in Python, MATLAB, C++, or Fortran 90 for problems involving thermodynamics, kinetics, and transport processes. So the advantages, so the chemical, kinetic, thermodynamic, and transport calculations are automated by Cantera. So you can easily, very easily, incorporate detailed chemical, thermokinetics, and transport models. That's a big advantage. So you have heard a lot of fundamentals. We need proper thermodynamical data, for example. We need proper reaction mechanism and so on. This can be found in literature, and this can be found in proper format for Cantera, or you have tools to translate it, for example, from Chemkin. So you don't have to bother about this part. You just can use it and learn a lot, and you don't have to bother about so many numerical problems because it's very stable. I focus here on the Python realization because the advantage here is the post-processing to the production of proper output is very easy as the proper libraries are installed here, and it's quite helpful again. So if I, for example, have to review a paper and I have some question marks, a lot of things I can easily simulate using such a simple tool, and within minutes I get the information I need. For example, is the velocity really increasing, the flame velocity, when I increase the amount of hydrogen in the mixture or not? Some things you can easily check without too much work. So I will not go here into the details, but there are excellent tutorials for Cantera you can find in the internet. So I have given the links necessary here. So there are different ways to install Python, Cantera in Python. So I don't go here into the details. It's just for your reference. Actually, for me, most complex thing is here the installation of Conda. As far as I know, the Anaconda distribution is eventually no longer supported, or I'm not allowed to use it behind our firewall. But the Miniforge installer solution works quite well, and this is the one I recommend here. So, and for our discussion today, I just have two examples. When you go to the web page of Cantera, you find a lot of reactors you can use, and a lot of tutorials, a lot of examples, and I just will focus on two realizations here. But I think if you understand the principles, then it's easy to use any other reactor any other class in Cantera to examine your specific problem. So I will focus on the batch reactor, so Cantera ideal gas reactor class, and on laminar burning velocity, how to calculate laminar burning velocities using the class Cantera free flame. So you can find a lot of reactor types in Cantera. So Professor Sahoo has shown you yesterday some reactors, constant pressure, constant volume. So we are talking about 0D simulations here. So you solve your equation as a function of time, but there are no spatial dependencies. So the assumption here inside this reactor, everything is homogeneous. So there are no derivates in any of the coordinates. Everything is homogeneous. So you just have to describe your equation system or the dependency as a function of time. So you can have different reactors here. So for example, here we see a continuously steered tank reactor. It's an homogeneous reactor. You have several variables which can describe your system. And in this case, you can have an inlet and an outlet. So a specific defined inlet flow with specific mixture composition, temperature, and pressure enters your vessel. Chemistry takes place, and then depending on your reaction and temperature and so on, you have a specific outflow. And so you can focus here on the boundary conditions you want to examine and the specific inlet conditions you want to examine. We can use such a setup also, or you can find it in the literature under perfectly steered reactor, and it can be used also for jet steered reactors, which the specific reactor we will learn, or we'll get some more information about this tomorrow. But I will go back to this batch reactor.
Sir,
Yeah.
could you have some examples on those reactors?
Pardon?
Could you have some examples on those reactors, some real life applications?
What do you mean with examples?
Examples of batch and continuous steer reactor and perfectly steer reactor, jet steer reactor.
Okay, so these three here are represented by this image. So you have a 0D system, homogeneous system, where you have some inlet flow and an outlet flow. And you can define your boundary conditions here, and you can define your inlet conditions. And I will explain it with the batch reactor more in detail what I mean here. And maybe then afterwards you can please ask again if something is missing. So the system, the two most simple system Professor Sahoo has given us yesterday were the constant volume reactor and the constant pressure reactor. That means you have a closed system filled by your homogeneous gas mixture, and then you at a given pressure and temperature, and then you solve your set of governmental equations. So in case of constant volume, you say, okay, volume is constant, temperature increases, number of moles is changing, so temperature has to change. Pressure has to change when we look at the ideal gas law. Volume is constant, pressure has to change. if you have a constant pressure reactor, the volume is changing as a result of your chemical reactions. So, and here in this example, so we will learn all the numerical details next week. But we consider here 4 state variables: the mass, the reactor volume, the temperature inside, and then for all the species we have one equation concerning the mass fraction of the species. And the advantage of the constant volume reactor is the total mass stays constant. There is no inlet, inflow, no outlet, so no change in total mass. So of course we neglect any wall reactions and so on. So it's just an homogeneous system, and the volume is constant, so there is no change in volume. And the energy equation is represented here with the temperature. You can normally find this also as represented by the inner energy, sometimes as using the enthalpy, but here we use the temperature, and the temperature change only depends on the chemical reaction, the heat, the chemical energy transferred to heat energy, or transformed to heat energy. And then of course we have a change, temporal change of mass fraction here, and this depends on the chemical rates we have, this omega dot. This is described by our chemistry, and Wk is the mole fraction at a specific time. So it's a quite easy system, and at the end we have a change in temperature and we have a change in mixture composition if you use this simple setup. And it's really simple. We talk about seconds. Even if you use very large, very complex reaction mechanisms, within seconds you can get your result. So it looks, for example, like this. You have, for all your variables in your system, you get the solution as a function of time. Again, it's a 0D simulation, so no spatial dependencies, no coordinates x, y, z, just the result as a function of time. Here, temperature, and for 3 selected variables, you can see the different behavior. So the system heats up and reaches the final adiabatic flame temperature. So OH forms in the flame front, so after ignition takes place, and as due to the fact that we have a high flame temperature, we still see a lot of OH in our exhaust gas. Hydrogen is formed during the ignition process, the atom, hydrogen atom, and then it's used by the chemical reaction. So here ignition takes place and then it's reduced. And here, of course, it's a hydrogen combustion simulation. Hydrogen at the inlet, ignition takes place, hydrogen is consumed. All this information we get quite easily, and most often we are interested here in, for example, the ignition delay time. How long does it take at a specific inlet condition? So at given mixture composition, pressure and temperature for the system to ignite. How long is the time between 0 and this increase of a specific variable? Because when this is a quantity we can measure easily in our experiments. And what the kinetic guys do is they develop their big reaction mechanisms, and at the end they compare the calculated ignition delay time with the experimental one, and then they check, okay, I have some deviations here. I have 1000 elementary reactions. Which of them are really important for this specific problem? They can perform some specific tests and so on, and this we will discuss today, just to give you an overview of the tools we have without having all the details you need to understand, but of course this will come in following lectures. So here, ignition delay time. On the left you can see an experimental result from I think it's from an RCM, rapid compression machine. So we compress a system. That's the first pressure rise we have here on the left. We compress our system in this rapid compression machine. So when we compress a system, of course, temperature increases. So chemistry needs some time. Competition between the chemical processes and, for example, heat loss to the wall and so on. But then after specific time here, around 700 microseconds, the system ignites, the pressure increases. In this specific experiment, they also measured the chemiluminescence of OH radicals using an optical sensor. So you can see, okay, no OH, no OH, no OH, and suddenly you can see an increase of OH. So here ignition has taken place. And that's the important thing if you want to examine some work in literature, want to perform similar calculations to see is my mechanism good enough or so on. You have to use the same criteria for ignition. So you can find literature where they define the ignition delay time using the difference in the pressure signal. So here first increase, second increase, that's the ignition delay time. Here in this example, giving this paper here, they focused here on the OH signal. Maybe 50% of the maximum OH signal is defined as the ignition delay time. Or you can find in the literature something like this. So you examine the maximum slope of your OH signal, and then you use this line here to check, okay, at OH equals 0, here at that point, there is my ignition delay time. So you have a lot of different definitions. We will see it later. There are also some papers where they use the maximum. When the maximum concentration is reached, that's my ignition delay time. It's always important to use the same definition to compare your results. But again, ignition delay time is defined as the time between reaction starts and finally an ignition takes place. So, and here's one example as from a tutorial of Cantera. So we have this here ignition delay time as a function of 1 over T or 1000 over T. So temperature increases from here to here, and we have seen it yesterday. We would expect a linear decrease if we consider an Arrhenius equation, because we have a logarithmic scale here. However, we see this change of ignition regions due to chemical reasons, as we have discussed yesterday. So we have one specific regime here, then we have here another regime, and finally in the high temperature area this H plus O2 leading to OH plus O reaction governs the ignition delay time. So in here we talk about this negative temperature coefficient. Even though the temperature is increasing, the ignition delay time decreases due to chemical reasons. And in this paper here, they have performed numerical calculations and compared the calculations with the results. And in the tutorial, you can get this mechanism, do your own calculations, and compare your outcome with their paper. So what we need to do to perform such a calculation. So here at this link you can find this tutorial which I want to discuss with you. So, and if you have any questions right now, or you go home, try it at home, find some errors, of course we can discuss it later on. So it's a typical classical setup. First we have to load some libraries. You can use different integrated development environments, IDEs, so PyCharm, Jupyter. There are different possibilities to use Python. You can also use it directly. But first of all, you have to import some libraries here for data handling, and of course Cantera has to be included too. Then here we use Matplotlib for the output of our figures. Such a comfortable tool. So I have started with GNUplot, which is also excellent, but this is much easier to use. So you have a lot of functions to represent your results in a plot after the work you have done, in very, very easy solution. Okay, what we need? Okay, we have the tool, but of course we need the inlet data. And so in this example there is a mechanism given. Of course, when we follow this link here, we'll come to a web page where all the data is given in this classical ChemKit format. So we have the thermodynamical parameters, which we need for enthalpy, heat capacity, entropy for each species. We need to know this, of course. Then we have the transport parameters, which we need for heat conduction and diffusion processes. Of course, we have a 0D calculation here. We don't have to bother about this part. And finally, you can download the chemical mechanism. This is not the format we need. We need an YAML file. That's a classical input format for Cantera. And of course you can download this and find your own tools to convert this if necessary. But of course you can also find this specific mechanism already in the proper format. And that's very important. This has a specific format. You can define several phases. So for our examples today, we always only have one phase. And each phase consists of reaction species and elements. So we have a specific phase, then we have species, and then we have reactions. And these have a proper format. Normally you don't have to bother about it because you only use this. But of course this has to be in a correct format, otherwise your simulation won't work. So for this example here, you can see 160 species as a list. The elements are given here, so nitrogen, carbon, hydrogen and oxygen. Some keywords here we don't have to bother about today, but so that's the definition of our phase. And then for each species we find the thermodynamical data we need. So we have here nitrogen. So then for the thermodynamical data, okay, a specific model, temperature range. That's the way you normally find these data. You find 14 variables or 14 data points. 7 for the low temperature case, so in the range here 300 to 1000, and 7 for the high temperature case, 1000 to 5000 K. So, and these 7 data points are used then to describe or to calculate the enthalpy, heat capacity and entropy of your molecule, in this example, for this example, nitrogen. How this is done we will learn later, but this is the idea behind it. So we have the data we need to calculate the thermodynamical properties for all of our molecules. So we have everything we need here, and then at the end, of course, we need our reactions. So 160 species. I don't know how many reactions in total. And there are different types of reactions involved in Cantera, or this YAML file. I have just explained here 3 different formulations. Of course, you can find several more for specific problems. So the classical way is the modified Arrhenius form. So K is equal pre-exponential factor T to the power of B, and then the activation energy. So when we look here, we have this equation CH4 plus H gives CH3 plus H2, and here we have A, we have B, and we have the activation energy. So these 3 parameters we need to solve the reaction rate as a function of temperature for this specific equation. Then we have 3 body reactions. So you have asked yesterday this M, what does it mean? So here we have it, H plus CO plus M, a colliding partner, M, gives HCO plus colliding partner. This does not change. It just takes part in the reaction, but it does not change. So, and the colliding partners here can be H2, water, carbon dioxide and CO. And you don't want to solve this equation for each of the colliding partners, so you sum them up. So the total concentration of M you use in your equation is a sum of the concentration of the species in the specific volume and the efficiency. So the efficiency is given here by the numbers. So water is a very effective collider, and hydrogen not so effective. we also have, as we have seen yesterday, a pressure dependency. And here you can see a specific realization how to examine or calculate your reaction rate depending on the pressure you are using. So it's a specific realization. I don't want to go here into the details because it's something, it's very complex, and it's more easy to discuss it maybe again when we come again to the numerical part. For this tutorial, I would like to skip it because there are different possibilities here, but it follows a specific format. So you can calculate your reaction rate as a function of pressure and temperature at the end. So then, okay, we have imported our libraries we need for the calculations. We have our mechanism. Okay, then we need to say our tool, okay, at which initial conditions we want to perform the calculations. That means what is the temperature, what is the pressure, what is the mixture composition. So in this we have here, we say reactor temperature, reactor pressure is 1000 Kelvin, 1013 or 1.013 bar, 1013 millibar, and we can, and that's really very helpful with the other tools I know. Compared to the other tools I know, you just use this function set equivalence ratio, phi equal 1, you define fuel, you define oxidizer, and he calculates automatically for you the mixture composition. So I don't know it for heptane here, N-heptane, what is the concentration at phi equal 1? I think it's something around 2 point something volume percent. But so this is done automatically. At the end you have the mixture consisting of N-heptane, oxygen and nitrogen, representing a mixture phi equal 1. So you can change your number here. Of course, you also can give the concentrations or volume concentration you want directly, but this is very, very easy to use it in this way. So we have everything we need. We have the initial condition of our system, we have the mixture composition, we have the temperature and pressure, and we have the reaction mechanism, so we can say solve the system. So this is done here. We call this class here ideal gas reactor, and we solve it as a function of time, or the result is then here in this vector here. But okay, then we have all the data to get the plots I have shown you. So at the end we have solved our set of differential equations as a function of time, and we have temperature as a function of time, and so on. But what we want to know is ignition delay time. So here in this example they have defined a specific function, and here ignition delay time is defined at that point where we get maximum concentration of a species, and the reference species here is OH. You can use, of course, any other species. Again, it depends on the criteria you can find in the literature when you want to compare your results with the one from literature. And then you just start the calculations, and here you call your function ignition delay time, which gives you then the ignition delay time tau. That's it. Quite easy. there is one important point here, the estimated ignition delay time. So when you, for example, want to calculate the ignition delay time of hydrogen in air at phi equal 1 from 800 to 2000 Kelvin, you of course change the ignition delay time by several orders of magnitude, from microseconds maybe up to seconds. And if your estimation is here too slow or too small, and your chemistry takes too long, you cannot find an ignition delay time. So you have to play with this number here if you want to get your ignition delay time. So do not get confused when there is no result. Most often this number was just too small. Your system needs longer than you have expected. So here then, until the time is smaller than the ignition delay time, he's doing the loop, and at the end he stops. Then okay, here some specific information to perform at the end this nice plot. So here we have the ignition delay time, or we have a plot of the mass fraction of OH, and this point here, the maximum, is defined at the point for the ignition delay time. So for one specific configuration, pressure, temperature, mixture composition, we have now the ignition delay time. But when you remember the plot I've shown you, we have plotted the ignition delay time as a function of temperature. So of course we have to do this very often, and that's quite easy. You can define a list here. So we say here, I think there is an error in the tutorial. So I think from 1800 to 1000 we want to get the ignition delay time with a step width of 100 Kelvin and temperature of 975 to 475 Kelvin. We want to have a smaller step width, so 25 Kelvin. So for each of the points here, we want to get the ignition delay time. So then here is a vector which considers the change of ignition delay time as a function of temperature. So for the lowest temperatures, we say, okay, maybe 100 seconds is what we estimate. For the intermediate temperatures, 10 seconds, and for the high temperatures is quite fast. Of course, this is an estimation. At the end, you have to check, is it right or not, and maybe have to adjust it and perform the simulation again. But again, we are talking about seconds. The calculation itself is not a problem. So then you get the tau. Again, for each configuration, we use the same mixture composition here, N-heptane in air, phi equal 1. And then we just have a loop over all of our temperatures we want to examine, and get for each temperature our ignition delay time. So we do not change pressure and mixture composition in this example, but if you want, you can also have a loop, additional loop about change of temperature and an additional loop change of mixture composition. Whatever you want, you are free to change it. At the end here we get a vector which for each temperature gives us, or includes for each temperature, the ignition delay time we are interested, or we want to yield. So that's the output of the calculation. And finally, here are some details concerning the plot. So this is the outcome of our simulation, which looks not so bad when we compare it with the initial plot from literature I've shown you. So, of course, the mechanism comes from this paper. So you can see here, we also see this influence of the negative temperature coefficient. Within minutes, we can set up our system in a way that we can get the same results the authors have presented in the paper. So it's an excellent example for this specific setup. So, okay, now we have talked about the example, and that's a classical way. When I start to use Cantera, I take such an example and play with it. First, I do the same calculation and check, do I get the same results? Is everything working properly? And then, for example, I change the temperature, I change the pressure. So what is the influence? And if I'm confident then with my simulation setup, I use it for specific topics where I'm interested in. For example, we have done here some research of the dependency of the ignition delay time from mixture composition concerning ammonia air and ammonia hydrogen mechanisms, hydrogen air mixtures. And we were interested in the dependency of the outcome concerning several mechanisms you can find in literature. So ammonia is now quite popular nowadays, and you find dozens of mechanisms, and you find dozens of papers, and each of this paper has its own favorite. So for their specific experimental condition, this specific mechanism was the best. So it's quite hard to say at the beginning which one is the best for our specific configuration. Therefore, we played with a different list of mechanisms here. They have, you see, a quite different number of species, from 32 up to, or 31 up to 128 species, and a lot of also different number of reactions are included. So because all these mechanisms were developed for a specific aim. Then, okay, we also changed the mixture composition. So for this ignition delay time, we compared our results with RCM measurements. And here you see they have used quite high amount of argon and only very small amounts of ammonia and oxygen. But we have here 3 equivalence ratio from 0.5 to 1.5. So further details can be found here in the paper, in these 2 papers. But we were now interested, okay, we want to compare these mechanisms at these specific conditions with the results given in literature. So can we get the same results, or do we see something different? So we have the same setup here. So we have to import our libraries. We have to import here also Matplotlib. Then, okay, for this example, I have here one specific mechanism from the list I've shown you before. Again, our specific inlet, starting conditions, temperature and pressure, 1630 Kelvin and 3.5 bar, following the literature we have. And here the equivalence ratio for this specific system I've shown you. So 90% of argon and ammonia and oxygen representing a mixture of phi equal 1. So everything again is calculated automatically here for us. So then here I've had the output for some of the results here, just to double check is everything correct here. And then I start my calculation, get again time history of all species, or and temperature and so on. And in this case, the reference species is nitric oxide, not OH as in the example before. And I have a different function here, that was the main work, because in the literature the ignition delay time was defined as 50% of the maximum. And so we have to use the same criteria in our calculations. And what we do here is, of course, first we find the maximum, then we find the next grid point near to the half of the maximum, and then finally we have an interpolation which gives us the time exactly at the half of the maximum. So then we have this, the same criteria in our simulation compared to the experiment from literature. So again, we start our calculation. We have to again to consider the estimated ignition delay time, and finally here we get our ignition delay time tau. So here, for example, I show you the time histories for a lot of different simulations. So it's phi equals 0.5, 1 and 1.5, and here you can see for all the different models we have used the NO mole fraction as a function of time. And you see, of course, just in one picture, a lot of discrepancies. So each reaction mechanism is maybe perfect for a specific condition, but is maybe not the best one for our specific condition. So you see large discrepancies here, NO as a function of time. But what you, for example, can see is here we have a lean mixture, phi equal 1, stoichiometric mixture, rich mixture. And what is interesting to see, the amount of NO reduces. And this is something, of course, we know this is what we have expected. So if you have slight rich mixtures, you get the minimum of NOx formation. Therefore, this is something, of course, we could expect, but we have to check, is the outcome we see here consistent with the literature, or have we done some errors? So here we have now, so in this example we have the high temperature cases over 2500 K or around 2500 K. So ignition is very fast. Here we are around 1600, 1700 K. So ignition needs much more time. And here, of course, you see differences not only in the maximum amount of NO, but also in the ignition delay time. Again, different reaction mechanism optimized for different configurations gives totally different results. And when we then plot, for example, here NO max as a function of temperature. So for all the simulations we have done, we have taken now NO max and plotted as a function of temperature for these three different mixture compositions. You can see big deviations comparing the mechanisms. So this is, of course, something we can expect, but this is something you have to do when you start with a new system. You cannot just take one mechanism and say this will work for me. First you have to check. No? You have to perform such simulations, and then you have to analyze the results here, which one is the best for my configuration, or what we may see later. So after the break, what is necessary to optimize one of the mechanisms for your specific configuration. So when we come to the results here, so first of all, you have seen different mechanisms give different results, but all of them more or less shows the same trend. So from lean to rich mixture, we reduce the maximum amount of NO, which of course we can expect. And here we have also a plot for the ignition delay time, or the table for the ignition delay times when we change the amount of hydrogen in our mixture. And I just plot them here directly. So again, here we have different mechanisms, and here it looks much better when we compare them. And here you see the ignition delay time as a function of temperature for 5% of hydrogen, 10% of hydrogen, 20% of hydrogen. And what you can see, and this is what we would expect, if you increase the amount of hydrogen, the ignition delay time reduces. So, and finally, that was the idea behind this work for us, to use Cantera to calculate the ignition delay time using several mechanisms to learn more about the influence of hydrogen on the ignition of ammonia hydrogen air mixtures. And finally, just to complete this part, so HOMREA is the in-house tool I used in my PhD thesis already. It's just another tool to solve the equation system we have. And you see there are some small differences, but this is mainly due to numerical reasons. So we can use different tools. We do not have to use only Cantera. And finally, this was just a double check, is everything okay with Cantera, or have we done something wrong? So we get the same results, and so we were really confident with it. So now we have seen that we can use Cantera to perform simulations. That is very important to consider, do we have a proper reaction mechanism here, yes or no? And then we can use it, for example, to examine some fundamental changes in our parameters. So for example, what is happening if we add some hydrogen? Here we have focused on ignition delay time, but for example, you can focus on formation of NOx. So ignition delay time may decrease, which is maybe useful for our application, but also NOx formation can increase, which is then of course not useful. So these parameters you can easily examine without performing expensive 3D calculations in advance to find your optimum setup. And here we used it then further to examine the mechanism itself. So And we use here quite simple sensitivity analysis. We want to examine how does the ignition delay time change if we change our elementary reactions. So we have a list of hundreds of elementary reactions, and if we change one of them, we just say the K value, the reaction rate doubles. How does this influence our system? Has it any influence at all? Does it change the ignition delay time? Yes or no? And and here we use the simple relation. So the temperature, of course, when we look at this Arrhenius term, temperature is in the exponent, is very sensitive concerning the ignition delay time, is very sensitive concerning a change in temperature. So if we change the temperature, we change the ignition delay time, and in a way, so an increase of temperature decreases the ignition delay time. So that means here, if we change this parameter to change the temperature, it directly changes also the ignition delay time. So we looked here now on this sensitivity to get information about this sensitivity. For these mixtures here, again, argon mixtures with some amount of ammonia and oxygen. And so this is the outcome you get from such a calculation. You have this normalized sensitivity here, so from 0 to 1 or from -1 to 1. And we just plotted here the most sensitive reactions. So we have for each reaction K, we have done this. We have compared the initial ignition delay time without any changes with the ignition delay time we yield when we change one reaction. And this is then the plot of the sensitivity, and here you see H plus O2 again, so my favorite reaction. So the ignition delay time is very, very sensitive, of course, concerning this reaction. But also we see here one specific ammonia reaction. H plus NH2 plus M gives ammonia plus M. So the system is also very sensitive concerning this reaction. And if it's positive here, so if we increase the reaction rate of this equation, it decreases our ignition delay time. And here we have an example. Okay, if we increase this reaction rate, it decreases our ignition delay time. So that's a tool to examine more or less the reaction mechanism. We have thousands of reactions, but at the end we find 10 of them are important for our specific configuration. These 10 we need to know exactly. For all the others, we can guess some rough numbers. The result is not depending so much for this specific configurations on them. So here we can optimize it. So this we have done for several. Here for the amount of, or the equivalence ratio. Again, my favorite equation, H plus O2, is in this list, and one specific, ammonia reaction. And now we have just taken one specific mechanism here and changed the reaction rate in this specific mechanism, just to show you the result. So if we change the reaction rate here, of course, then we change the ignition delay time, and we have just done it very simple. We just multiplied it by a factor of 2. We just said, okay, this equation here is now 2 times faster than in the normal or given mechanism. And you see again, if we just change these 2 equations, you can see big discrepancies here. When you compare the modified model with the Shrestha model here. So NO max, you see a big change here. The maximum amount of NO is very sensitive concerning these equations, but also the position here, which then gives us the ignition delay time. So I would like now to make the break. I have explained to you how we can use quite simple numerical tools. So a 0D calculation, which gives us solution of the temporal development of our equation system within seconds on a normal personal computer, can be used to get very fundamental insight in our chemistry we are using. Of course, most often, if you are not interested in the development of your reaction mechanism, you are not looking on such specific parameters I have presented you. But very often, you just change your initial conditions, pressure, temperature, mixture composition, to find your optimum mixture configuration, which you then may use in a very complex, very expensive 2D or 3D calculation. Do you have any question until now?
So how to know about all the elementary species or elementary reactions?
Sorry, some background noise here.
So there are elementary species.
Any what?
And in every reaction there are a lot of elementary species.
Yeah.
So how to know about all the elementary species? And what about all about elementary reaction? How to form all the elementary reaction? Because only we know initial reaction and final reaction. What about other rest? How we know about that?
This I have shown you in the last lecture. So you can use different tools. So you have CH4 plus O2 gives water and carbon dioxide. That's the global reaction. And then you can do it based on experience. So you know, okay, we have CH4, we have oxygen. Okay, what are the possible intermediates? You can write them down. You get a list of thousands of species. And then you can say, okay, this is not important, this is not important, this is not important. So just try and error plus experience. So you can develop a mechanism, and then you can check it. Does it work or not? So this is then supported now by quantum mechanical calculations. So for each of the calculations, you get detailed information then, or reactions about the activation energy and so on. We pay exponential factor. And nowadays we do not do it by hand anymore. We can use something like this reaction mechanism generator. And you can look for this in literature. It's more or less done automatically. But then, of course, you'll get a very extensive list of reactions and species. And the art then is to optimize the setup. So does it answer your question? Yeah?
Sir, one more doubt. Is it possible to calculate the temperature of the product at last we get? Product temperature, reactant temperature and pressure we already know, initial condition.
Mm-hmm.
What about product temperature and product pressure at last we get?
So this Professor Sahoo has explained tomorrow in the morning when you consider this adiabatic flame temperature. So the flame temperature depends on the initial conditions, pressure, temperature, and mixture composition. So I want to go to this list here. So we have not so much plots here. For each initial condition we have, we get the flame temperature here, for example. And I have shown you this plot temperature as a function of time. For example, there you can get this information.
To calculate the ignition time, so we are taking the OH radicals most of the time.
Mm-hmm.
So is there anything special about OH radicals? Why in maximum cases we are considering OH radicals?
Because it's easy to detect in the experiment. So H radical is much better. As I have shown you, there is an increase of, maybe I can show this plot again. On the left you see there's an increase, strong increase, and then it decays again. So it would be better, but it's much harder to detect. So for OH we can use chemiluminescence, so just measure the emitted light very often, and this we will learn maybe tomorrow or later. We can use specific laser diagnostics, so-called laser-induced fluorescence, and OH is very easy here. For H, we have to use specific, very complex configurations. 2-photon laser-induced fluorescence, so it's much more complex. That's the reason why we use OH, because it's so easy.
So, my question is, so far what we have seen here is about liquid as well as gaseous fuels. What about solid fuels? For example, in big thermal power plants, they may use coals and woods. So is it possible to apply the software to analyze solid fuels?
I don't know it specifically for Cantera. I think it was done before, and you will find proper examples here. I have done it myself using another tool, but it's a simple one-dimensional setup. How can I? Pen. I try it here. So we have our coordinate, and we can say here we have our particle. our solid particle. So here we have gas phase, and here we have solid phase. And then the easiest solution is just to simulate the gas phase. So you can, for example, say here you have high temperature in the solid phase, and at the beginning the gas phase is quiescent and cool. So 2000 Kelvin, 300 Kelvin, for example. And then, of course, as a function of time, you see development of the temperature profile here, and after some specific time you see the ignition. So because for most of the solid fuels we have, the combustion takes place in the gas phase. So they vaporize, and then combustion takes place in the gas phase. There are very few compositions where you have direct burning of the solid phase. So that's the simplest setup. You define your solid phase, you define your gas phase, and reaction take place in the gas phase, and then you can also include some wall reactions. So the gas phase hits the surface, and something is happening then with them. And if you want, but you can also then incorporate reaction in the solid phase. Or if you have a droplet, you can have a droplet which evaporates, and you have reactions in the gas phase and the solid phase. Everything is possible with just one simple 1D calculation. Does it answer your question? Any further questions? Then we have lunch break. When do we continue? 2:30 again? Good, thank you. It's on.
On his.
So in Germany we need at least 5 participants. Otherwise we can cancel the lecture.
Oh. But here we can.
We have 1 video camera. Okay, I will start. Yeah, then we can finish earlier. So, welcome back to the 9th lecture of our course, and in the morning I've presented you the tool Cantera and how we can use it for calculation of ignition delay time, and in this session we will continue. But before this I want just to give you a short reminder. You have an excellent tool here. You can calculate everything without much problems, but always be skeptical. So the difference between good students and bad students is, do they ask, is it correct what I see or not? So the typical student which comes in my office says, here, this is my results, and when I ask, is it correct? Of course, it was calculated, so it has to be correct. The mathematical tool maybe has calculated something, but you don't know if it's correct. You could use wrong initial conditions. you could use wrong mechanism, which is maybe optimized for 1 bar and laminar velocity, but you want to calculate an ignition delay time at 40 bar, and so on and so on and so on. There can be so many errors, and you always have to double check. Here, just an example, we increase ammonia from 0.5 to 1.5. We increase the equivalence ratio, we increase the amount of ammonia. Nevertheless, NO decreases. So, of course, then we checked literature, and then we found out, okay, this is something we can expect. But the normal student comes with this plot in my room, and I ask him, does it make sense? And when the answer is, of course, it was calculated, so the computer has done it, this is not the correct answer. Check it, check it, check it. That's always impossible. You get so much data with these tools, but do not just rely on the output. Make always a double check. Otherwise, you produce just rubbish. You cannot use it. So, when we go to the laminar burning velocity, so in the morning we have had batch reactor, 0D configuration. Here we have a 1D configuration. So we have a flow from left to the right, and so we have cold unburnt mixture on the left hand side, and then we have the reaction zone, and then we have the hot exhaust gas. So, and this can be used to calculate the laminar burning velocity, LBV. The idea is, if you, for example, want to keep the flame at a fixed position, and your flow velocity is faster than the flame velocity, your flame will move to the right. If your flow velocity is slower, it will go to the left. So your inflow velocity has to have the proper value that your flame stays at a constant position, and this is your laminar burning velocity. So the velocity of the cold unburnt mixture, which is necessary to have a fixed flame position, this is the laminar burning velocity following this example here. So it's a one-dimensional system we have to consider. So we have one coordinate, and we are interested in a stationary solution. So we can, of course, keep these values here. The temporal derivatives are normally 0. There are different solvers. So you can use stationary solvers, but there are also instationary solvers. So at the end, your result won't change. You get a stationary solution. So there are different possibilities to realize it. So I show here a set of differential equation for an instationary solver. So we have to consider mass flow again. Here we have energy equation as a function of temperature again. And here we have this solution or the equations for the different species we have to consider. So this is the equation system which is behind our one-dimensional problem here. Unburnt mixture, flame zone, exhaust gas. And here you see some of the variables Professor Sahoo has discussed in the morning. So CP, for example, heat capacity, we need it already for the homogeneous mixture. So enthalpy heat capacity, entropy. But here we have in addition a diffusion flux, and here we have heat conduction. So we also need some molecular transport parameters that to describe the heat conduction and the diffusion properly. So we have a multi-component system. This was explained by Professor Sahoo in the morning. So we need some more data than today, and we need, of course, a different setup. So again, I will start with an example you can find here. So how to calculate the laminar burning velocity simulating a freely propagating adiabatic 1D flame using Cantera. So of course what we need to know, we need to know the density and the temperature at the inlet condition. So mixture composition, pressure, temperature, again we need to know. So pressure is constant all over the regime, and so temperature changes, density changes of course, and velocity changes, because finally velocity times density is constant for our system. So if we decrease the density in the due to the combustion process, we then have to increase the burning velocity, the flow velocity. So, and here we can use a specific class from Cantera, so Cantera.freeFlame, and so this is a model for this laminar flame speed, and we need some specific input parameters again. We need to know the temperature of the unburned gas mixture. We need to know the pressure, of course, and the composition. So to define our inlet conditions. And then we need to have a proper chemical model. And another point is the domain length. So we have a one-dimensional flame, and the flame front has maybe a length of tenths of a millimeter if we have very fast combustion process, but it can also extend some centimeters for very slow flames. So the length of your computational domain has to match here more or less. No? Should not be too long, not too short. So, and then of course we have quite some simple commands to compute the laminar flame speed. So again, we need to load some libraries here. We here have some parameters for our plotting. And then we define inlet temperature and pressure of our system. So nearly ambient condition, 300 Kelvin and 1.013 bar. We have now this well-known GRI mechanism, which we use again as an WAML file. And for this example, we have stoichiometric methane air flame, so 9.5% methane in air. So again, simply calculated using this function here, set equivalence ratio for 1 for methane in air. Here we have the flame domain, so it's 14 centimeters, for example. This number is not so important, but it should be checked, and you should not use 4 meters here when you have a very fast flame. You should not use 1 millimeter here if you have a slow flame. Better double check. Look at the results, not only at the value of the flame velocity you yield, look at the profiles too. Double check, always double check. Then here we call already the solver. Okay, here we have some parameters for the solver, and at the end we get our flame velocity. That's it. Quite simple, not much more complex than the example we have seen in the morning. And here we get a typical result. The temperature now is a function of distance. So cold unburnt mixture, and after a given distance we reach the flame front, and here combustion takes place, and finally we get the exhaust gas here with the adiabatic flame temperature. So, and we can then also plot species, here just the comments from the examples. So then we have here methane as an adduct, and the products water and carbon dioxide, which are normally not so interesting. More interesting are the intermediate species, H, OH, and so on, which then normally have, so H for example here in the region of the flame front, the maximum. So what we add here is also a sensitivity analysis. So we have discussed it already in the morning. When we change our reaction rates for each of our elementary reactions and do the calculations again. So we take equation number 1, change it by a specific factor, and calculate again, here for this example, the flame velocity, and compare the disturbed solution with the undisturbed solution. This we do for each of our reactions. So this is then explained here. So we have for M in range, that means for all the reactions we have, first reset them to the original value, and for each M just add a small quantity to your reaction rate. This here change it just by a small quantity, and again calculate the flame velocity, and then here the flame velocity is defined as flame velocity disturbed minus flame velocity undisturbed over the undisturbed flame velocity times the value of the perturbation we have performed. So again we have something like a normalized sensitivity we see here, and we can directly see which reactions are important and which are not. So here the outcome, again my favorite is here, H plus O2 gives O2 plus OH. So if we increase the reaction rate of this equation, we would increase the flame velocity. And so the flame velocity strongly depends on these reactions and so on. And again we only plot the 12 or whatever, the 12 most important reactions. From over 100 reactions, these 12 are very important concerning calculation of a laminar burning velocity. So again here we have to focus. If we know them very well, then the result can be very good. So again we have done this first to get confident with Cantera, and to check is everything working properly. Compare your tool always with literature, always with tutorials, to check if everything is fine. So and then we go back to the original problem we have had. We want to analyze ammonia air, ammonia hydrogen mixtures. Okay, in this case, of course, it's not the initial delay time, it's the laminar burning velocity. We have done it for a range of equivalence ratios, and we have done it for a range of pressures. And for one initial temperature and for one specific mechanism, because in this paper here they have also given their results concerning measurement and simulation of laminar burning velocities, so we can compare our results first with their results before we modify the initial conditions to examine our specific problem. And so this is the outcome. So here we see laminar burning velocity as a function of equivalence ratio at 1 bar and 473 Kelvin. And what we see, okay, near the stoichiometric composition, we yield the maximum velocity, something we can expect. And if we increase the amount of hydrogen, the flame velocity increases. Also something we can expect. So this is this example here. Maybe can we have a short break with the video? Because I have to upload another file. Yeah? Do you have any questions concerning the presentation I've shown you here?
Should I saved it?
Pardon?
Should I saved it? To people.
Again?
Saved it? Should I saved it?
No, it should just it should not be saved with changes. It can just be closed.
this a new PPT? Is this a new
Yeah,
PPT?
yeah.
Right? It's a new PPT, right? So can I exit it? The earlier PPT? No, can I exit it?
Yes, I put it there.
The second one.
L, oh sorry, there is some typo. This L minus 2. Can you click on it
Oh,
once?
this one.
Now you can copy it. Okay, so I've presented you now some results of the ignition of ammonia-hydrogen mixtures. And of course the question is why? Why is this of interest? And so I present you some results we have presented at the Ammonia Symposium. I think it was the first one in Bristol, where we have, and just close it, can close it, thank you. Where we first have discussed the dependency or the parameters we have to consider when we want to examine ammonia-hydrogen air mixture ignition by electrical discharges, by classical electrical sparks. So when we look at such a typical spark, normally concerning safety issues, for example, we focus only on the energy. So hydrogen has a minimum ignition energy of 17 microjoule, so a very, very low value, so it's very difficult to handle. Propane has a minimum ignition energy of 420 microjoule, so much safer to handle. And when we go to ammonia, we have an ignition energy, minimum ignition energy of 50 millijoule. So nearly 3 orders of magnitude more energy is necessary to ignite ammonia compared to a hydrogen air mixture. But of course, the energy value you can find in literature is always based on the energy stored in a capacitor. So it's the breakthrough voltage times squared times 0.5 times the capacitance of the capacitor. So we have just an energy value, but we don't know anything about the plasma we see here, and we don't know anything about the combustion processes and ignition processes leading to a self-sustaining flame propagation. So when you look at these numbers you have, 17 microjoule hydrogen, 15 millijoule ammonia, you always have to consider that these represents values where we have in 1 of 100 cases an ignition. So we are really at the border between ignition and no ignition, but this is not a sharp border. It's of course a statistical process too. So here, I think this is it's for propane, the example. We have several experiments here, and you have can find a boundary between ignition and no ignition cases, but of course it strongly depends on the experimental configuration. So this is important if you compare results from literature. It always depends on the type of experiment which was performed. And so here, for example, you see the probability of ignition near the minimum ignition energy. So 1 of 100 experiments should ignite. So the minimum ignition energy is somewhere here. So it is clear that there is, of course, also a large error on this number. So when we look at typical spark, okay, here we have the electrical energy. This we know, we can measure. But of course we have external circuit losses, which we may not know, and we have the spark discharge. So not all of the energy is not distributed to the spark discharge. Then we have a formation of the spark channel, and we have losses due to electromagnetic radiation, and we have cooling at the electrodes. Again, some joules are lost. Then we'll have a shock wave, which leaves our spark channel at a given time. First of all, some energy is then distributed to the surrounding again, and the spark channel itself is broadening from several micrometer up to several hundred micrometers. Then the question is, okay, which energy is applicable for the ignition process? And this is what we can vary, and the rest we have to examine. So from literature we know for hydrogen a lot. So hydrogen is examined very well. So we know the minimum ignition energy is 17 microjoule when we have a gap distance of 0.5 millimeters. So this we know from literature. This was repeated very often. For ammonia in air you cannot find so much data because it was not of interest very long. So you can find results here 14 millijoule, but you can also find 680 millijoule. Again, it depends strongly on the method you use. And here we have a result of work at PTB where we have varied the electrodes and the spark gap. And you see here, when we have a gap of 50 millimeters, we get our minimum value. At nearly stoichiometric conditions, so phi is equal 0.9, there we get the minimum value. It's 14 millijoule compared to 17 microjoule. So big difference, and we have had 0.5 millimeters for hydrogen in air, and here we have 15 millimeters. So this is the optimum gap distance. So now the question is, if we want to use in the future ammonia hydrogen air mixture for different applications. How we have to consider this minimum ignition energy as a function of hydrogen composition, because this is an important factor if we want to consider safety aspects. So how can we simulate it? This is an extension of the tools I have shown you in the morning. So here we use a classical spark. So here we have an 1D configuration again, and that's a cylindrical configuration. That means we have gradients only in this dimension, in R direction, and no changes in this direction. So again, we can use in one-dimensional configuration to represent our ignition problem. So we deposit energy here, and then we calculate ignition and flame propagation perpendicular to this spark channel. But we also have calculated laminar burning velocities, and we can also calculate extinction strain rates if we want. So we have a lot of different tools to examine the system in total. And if we talk about minimum ignition energy, this is the quantity we need to know. But when we look at the energy equation, you cannot find the ignition energy alone. It's always a quantity of density, because your energy is deposited into a specific volume. And as said before, the spark gap concerning ammonia is 30 times larger than the spark gap for hydrogen. So when we put now this number, so nearly a quantity, 3 orders of magnitude larger energy, okay, but this we can already divide by a factor of 30 concerning the energy density, because we deposit, in case of ammonia, the energy in a much longer, much larger volume. So this we have to consider here. And then, of course, the initial radius of the spark is of importance. So first, we have used a specific mechanism optimized at PTB from colleagues to perform the simulations, and we have used this mechanism, have compared our results with literature. So here we have the flame velocity, so 6.5 centimeters per second for ammonia and 2.3 meters per second for hydrogen. So quite confident comparison with literature. Here we have the extinction rate using a counterflow configuration. Again, our simulations at 5 different pressures compared with literature, sufficient result. And finally, here we have the ignition delay time, as a function of amount of hydrogen, which then reduces here drastically, and again compared to literature. So we were confident our numerical tools are working properly. So the mechanism was implemented correctly, and the set of equations we are solving were solved properly. So here we can define the spark. We use a specific profile here. There you can use So this is a factor of 8 we see here. Of course, you can use a square or linear relation. So in this energy, in this volume, the energy is deposited. And of course, the radius here is of importance. So we have varied the energy in the range of 70 microjoules to 40 millijoules. The spark length was in the range of 3 millimeters to 50 millimeters. And we used different radiuses here to examine the process, and also we varied the energy deposition time for always phi equal 1 mixtures at initially ambient conditions. So what was the outcome? So here you can see the flame front as a function of time. So in case of ammonia, pure ammonia, you see a very slow flame propagation. In case of hydrogen, we have a very fast flame propagation. And so, as expected, increasing the amount of hydrogen, the flame velocity increases. Here you see the amount of hydrogen atom as a function of time again. So you can see pure hydrogen ignites very fast, and here pure ammonia ignites very late for this specific configuration we've examined. So there was assumption that in case of hydrogen we have something so-called preferential diffusion. So hydrogen is a very small molecule, so it diffuses very fast. And preferential diffusion means that you no longer have a homogeneous mixture. So if you have a temperature profile, the hydrogen is moving faster to the hot zone than the ammonia. And so you have something like a hydrogen enrichment in your flame front. So this we can examine numerically. Lewis number equal 1 means all species have the same diffusion velocity. So there is no preferential diffusion, of course. Then we can say it's only for molecules smaller 15. So this is not correct here. Mole mass of smaller 15 gram per mole, and thermal diffusion for all species. And you can see an effect here, but this is after the ignition. So we can see here an influence of this thermal diffusion. So the hydrogen is enriched at a specific condition. We see here the maximum amount of hydrogen in our system. But the ignition takes place more or less at the same time. So this has no influence on the ignition process itself, or no significant influence. So then we looked at the radial profiles of selected species. So here we have the temperature profile. So we have a rich ammonia hydrogen mixture. Rich means we have 80% ammonia, 20% hydrogen. And here we have the temporal development of temperature. So at the beginning, of course, 300 K. And then we deposit some energy, it heats up, and then the flame front moves away from the hot spark channel into the unburned gas mixture, and the length of the energy deposition is 100 microseconds. So after 100 microseconds, the flame velocity, or the temperature decreases again inside the hot gas kernel, but here combustion has taken place, so the flame moves to the outer side. This we also can see when we look at this hydrogen, for example. Or even better here in case of the H atoms. I don't know why we have such an unusual plot here. But again, so this increases drastically in the hot region, and then after the end of the energy deposition, it decreases. And what is interesting concerning ammonia, so we have talked about OH and H for the hydrocarbons and hydrogen as a flame front marker. For ammonia, NH2 is a better flame front marker because the other radicals are consumed. We cannot see them so much. So here, when we look at the H profile, okay, we see where it is hot, where the energy deposition is, but we cannot see the flame front. But here we see it for NH2 very clearly. So here we see the outward propagating flame front. So only in the flame front we have some NH2, and in the cold and hot region nearly no NH2. So what is the big difference? So we have seen we have a much longer ignition delay time for the ammonia for this configuration, and so here we have again very rich ammonia mixture, 95% and only 5% hydrogen, and we vary the energy here, so 0.6 joule per meter, clearly just fast ignition. So the temperature here is dominated by the energy we deposit from the spark, and then here we have the adiabatic flame temperature, more or less we see. If we use 0.5, we heat it up, and then no ignition takes place, the system cools down. But we also see here some interesting cases, 0.54 and 0.55 joule per meters. So here the chemistry needs some time. It's not clear will the ignition take place or not. So here in this case energy was not sufficient, so no ignition takes place, it will cool down. But in this case here it then starts to ignite, which is also very unusual compared to typical hydrocarbons. But especially for hydrogen, you would not expect such a behavior. And this is, we can also see in the chemistry, here we look at the H atom. So after end of the energy deposition, we have for a very long time, we see a lot of H atoms, and at 4 milliseconds, nearly 4 milliseconds, we can see clearly differentiate between ignition and no ignition, which is a very long time period. Here this is a classical hydrogen example. Here we have 80% hydrogen, 20% ammonia, energy deposition, end of energy deposition, and then the final ignition takes place. This is classical, typical spark experiment. If the energy is not sufficient, it just cools down. And you see it more clearly here at for example, NH2 radical. In case of ignition, we produce a lot of this NH2 radical, and here we see the amount we have in the flame front. In case of no ignition, we produce nearly no NH2, and of course no ignition has taken place. So what is now the outcome concerning the minimum ignition density? So again, the difference in the minimum ignition energy is nearly a factor of 1000. 70 microjoule compared to 14 millijoule. But when we look at the density, we see, okay, we start here at this specific number, and we end here. You see it's maybe one order of magnitude. So what is the difference? The length of the spark is much longer, and what we have not considered here, which I will show you later in this lecture, if we use sparks with such a high energy, they are also much broader. So in typical spark for hydrogen, we are talking of a radius of the plasma of maybe 100 micrometer. Here in case of ammonia, the energy is deposited in a channel which has a radius of nearly 1 millimeter or even more. So we have much higher energy, but we have also a much larger volume where the energy is deposited. So the energy density difference is quite small. The energy density difference is quite small when we compare ammonia with hydrogen. This is very helpful if we consider to enhance combustion processes of ammonia, for example, in combustion engines. We have to add some hydrogen to enhance the combustion process. But you see, unfortunately, the ignition process is very sensitive. So small amount of hydrogen drastically reduce the ignition energy we need. Unfortunately, the flame velocity does not change so much in this area. So when we talk about applications with maybe 20% of hydrogen, it increases, of course, the combustion process, but it's so to come in the range of hydrogen, we would need much more enrichment of hydrogen. So I have shown you a practical example of the simulations we have discussed today in the morning and in the afternoon, extended with another model which we will discuss next week in detail. And I have shown you that, of course, we have used quite simple 0D and 1D calculations. So no sophisticated 3D turbulent flame calculations, but nevertheless, using these simple tools, we can learn a lot. We can examine the important parameters, and this is, in my opinion, much faster and much more reliable than using here, for example, an open foam setup. But of course, this always depends on the application you are interested in. So with this, I'm at the end for today. Do you have any questions?
So for calculation of the laminar speed or the laminar flame velocity, so we are using the equation which is dependent on your diffusivity, reaction rate and on-burn temperatures. Okay. So in experiments, so how do we calculate them? In practical sense, how do we calculate the flame speed? And what are the techniques associated with calculation?
You mean how to determine
Yes.
laminar burning velocity experimentally?
Yes.
So one possibility is to use a pipe and adjust the inflow velocity that you have a stable flame position. So then the velocity of the unburned gas mixture is your laminar burning velocity. But of course this is quite complex. There is a concept of a heat flux burner. Here I'm not an expert how this is working. This can be used to determine laminar burning velocities. Here I have to check the details and maybe can give you this later. A much easier setup is a classical combustion vessel, like you see here. So here you see an ammonia air flame ignited by a spark, electrical spark. And you can examine the flame front propagation as a function of time in such a configuration, and with some mathematics. So you do not see here directly the laminar burning velocity. You see more or less an overall global flame velocity. So you have an expansion of the hot gas kernel, and you have of course a curvature effect. You have at the beginning a very small flame ball which then increases, so the curvature reduces. But with so you can measure flame front as a function of time and then calculate from this the laminar burning velocity.
Okay, from that conical structure to the parabolic or the radius radial structure.
Pardon?
Once like it happens in the Bunsen burner, so it's first remains as conical, then it's becomes.
I think you can also use something like a Bunsen burner for this, but then you of course have to consider that you may have not an flat flame. Yes. Any further questions? Okay, then we can finish for today. Thank you. Warum sieht das so scheiße aus? So, do you have any idea why it looks so confusing?
That's overlapping, I guess.
Can you please reopen this? I have to check, so maybe I give you a better version tomorrow.
The size, I think this would be 16:9, the size ratio.
Yeah, but
I don't know why it's happening. I asked my senior, he didn't even know what's happening. But I don't think so it's an issue. I guess it's not a very big issue actually. So it's normal, it's happening. So it's okay. It's okay, fine
I will
actually.
give you tomorrow a better version which can be distributed. So shall we directly continue? Okay.
Yes, sir. In rockets, I've used hydrogen as a fuel. In rocket propulsion, we use hydrogen as a fuel, sir. Rocket. So, sir, it is in the liquid form. Liquid hydrogen along with liquid oxygen combined.
So the classical NASA rockets.
So, sir, liquid oxygen and liquid hydrogen.
You have to cool it.
Yeah.
So the
If you want to copy it,
liquid
if you want, you can take a copy.
liquefaction
Okay.
of air is a well-known process. So liquid nitrogen is the classical gas you have.
Continue.
So what are you doing? You
Finish
compress it to cool it.
There is one word,
So you have to expand it.
Yes, and there is one word cryogenic something.
Yeah, yeah.
So how we can do it?
So this is typical thermodynamic process. In the case of hydrogen, it's a little bit more difficult because you have to go below minus 200
minus
something
yeah.
degrees.
Yes, sir.
Yeah.
So like we can convert it from high temperature to phase change process, and after we have to make it certain.
This is the only problem of energy. You need 30% of the energy
Is it okay?
you have in the hydrogen to
सर्कल
get
सर्कल ओवरलैपिंग हो गया था 16:9 पे.
not very
Is it okay? Just can you
But
just
it's
check it?
Fine. I think circle issue.
Like
हाँ यार,
hydrogen
Wait.
production they are
I think it's
So
okay.
that was a rocket fuel. It was used, of course, NASA Saturn V rocket. Yeah, that's a common fuel.
उसको वापस
But
उसको
so in Germany, I think we have just one plant which is producing liquid hydrogen. There was an accident in the spring of this year. They have not solved the reason for the accident, so actually liquid hydrogen is very expensive to get. So do you produce it here in India, liquid hydrogen? You have on the space science program too, but they use solid rocket or solid rocket fuel.
Hello. Is it fine?
They import it. Maybe they import it from somewhere for using.
I think hydrogen oxygen is no longer state of the art.
So good evening to everyone. So good evening to everyone. So myself Kiran Kumar. So I am a postdoc fellow here. So under the mentorship of Professor Sahoo sir. So today's my presentation is on heat transfer enhancement using metal foam and its application in combustion process. So when it comes to any heat exchanging devices, its primary objective is to enhance heat transfer performance. So that is the basic things. So when we consider any heat exchanging, and to improve its efficiency, so that is the priority, it will be there. So that leads to a creation of novel technologies as well as optimization of the current existing technologies that is required there. So in order to do that, there are different techniques or methods are available. One is enhancing the heat transfer surface area. So by that we can enhance the heat transfer. Another one is we can improve the fluid flow characteristics. By that also we can enhance heat transfer. Then the application of nanofluids. So by that also we can enhance the heat transfer performance. Then improving the design of any heat exchanging devices. So by that also. And one more method, it is the introduction of porous media in the heat exchanging devices. So my research work, it is done by using porous media. So now we will see what is this porous media it is. So porous media, it is nothing but a matrix with interconnected voids. So what we can see it in this figure left side, so the skeleton portion of this object, so that we call it as a matrix. So that is interconnected by a voids. So that path that is available for the fluid to flow, that we call it as a pores. And that skeleton portion or matrix, we can call it as a ligament, or sometimes it is also referred as fibers. So when it comes to this porous media, so there are two types. One is deformable porous media and another one is non-deformable porous media. So as we can see this example of chalk, this is comes under non-deformable porous media, and this sponge, it is comes under a deformable porous media. And based on its occurrence, so natural porous media as well as artificial porous media it is there. So these are the few examples for natural porous media as well as artificial porous media. So our case it is heat transfer enhancing using metal foam. So metal foam it is artificially prepared. So for our requirement, for our specification according to our design, so we can prepare this metal foam. So that is comes under artificial porous media. And this metal foam, when it comes to this, two types are available. One is closed type, another one is open cell. So the first one, this is a closed type. So this is mainly used for energy absorption applications. So like car bumpers. So this is having a capacity to absorb impact load. Okay. So soundproofing. So for that also it can be used, and for thermal insulation purpose. So we can use this closed cell metal foams. And open cell metal foams, this is also a good energy absorb capacity, but mainly it is focused for to use it for heat exchangers to enhance the heat transfer performance. So this is having a pores, so which will allow the fluid to flow through it. So by that it will enhance the surface area. By that heat will be enhanced. Heat transfer will be enhanced. So this open cell metal foam, so it is a rigid sponge made up of metal or metal alloys, and it possesses some characteristics. So like one is pore diameter. So what you can see it in that skeleton structure, the pores, the voids that is available for the fluid to flow, that we call it as a pores, and its diameter. So it is not exactly a circular shape, it will be somewhat annular shape, it will be there. So average mean diameter it will be considered, so that we call it as a pore diameter. And what you are seeing is ligament, or it is also referred as fiber. So that diameter we can measure it, so that is fiber diameter or ligament diameter. And another property, it is pore density. So what is that pore density means? It is referred by as pores per inch. So PPI, pores per inch. Per inch, how many pores are available? So as you can see it in this second figure, figure A represent 10 PPI, B 20, C 30 and D 45. So if you consider first one, that is 10 PPI, means 10 pores per inch. So if the pore density is lesser, the pore diameter will be larger. If you go by higher pore density, that is 45 cases, so the pore diameter will be lesser in cases. So this plays a major role in the heat transfer enhancement. So pore density. The next property, it is porosity. So it is calculated as a ratio of volume of pores to the total volume. So that volume of pores can be calculated as total volume minus solid volume. So divided by total volume. By that we can calculate the porosity of that particular matrix. Another property, it is permeability. So it is the ability of the metal foam to allow the fluid to flow through it. So that property we call it as a permeability. So these are some of the important characteristics that is possessed by a metal foams. So when we introduce metal foam in the heat exchanging devices, yes, of course it will enhances the heat transfer performance. So that is what we have observed in the literature also. But what is the novelty of my research work is that, yes, of course enhances the heat transfer performance, but at the same time when we introduce metal foam, it will increases the pumping power, means the pressure drop also it will increases, so that we can't neglect. So anyway the primary object is to enhance heat transfer, but the increased pressure drop we can't neglect it. So if the pressure drop increases, we need to supply more pumping power requirement, so that is the loss, so efficiency will reduces. So we need to concentrate on that factor also. So my research work was mainly focused on that one. So to optimize this increased pressure drop with higher heat transfer rate. So in order to do that, I have used the application of second law of thermodynamics. So that is exergy and entropy generation analysis, that what I have performed. So my work is numerical work. So for that I have considered the geometry that is similar to the experimental that is done by Kamath et al., that is in IIT Madras. Okay. So this is the geometry, experimental setup, whatever they have. So at the center, so they have a heater. So beside that heater, aluminum plates are placed. Then beside that one, we will have a metal foam here. So from the bottom, so air will be circulated. So there is the anemometer to check the velocity of that one fluid. So air travels from bottom to upwards, so it carries the heat from the aluminum plate. So heat will be transferred. So in order to enhance that heat transfer performance, so metal foam is introduced in the channel. So this is the numerical model, this is my work. So similar to that experimental setup, I have created one model, numerical model, a vertical channel. So you can see it at the center, we will have a heater. So in the experimental setup, what they have done is they have considered one mica sheet. On that they have wounded nichrome wire. So they have created a heater like that. So in my case, so I have considered at the center of the channel, we have a heater. So beside that, they have also placed aluminum plate. I too have a placed aluminum plate. Its size is 250 by 150 by 3 mm. Whatever the dimensions they have considered, same parameters I too considered here. So from the bottom of the channel, air will be circulated, and whatever the aluminum plate, it is received the heat from the heater. So that will be transferred to the air by convection phenomenon, heat will be transferred. So that case we call it as a empty channel. So in order to enhance that heat transfer performance, what we have done is same case as that Kamath et al. We have introduced the aluminum plate. So aluminum metal foam. So that parameter what I have considered is 10 ppi. So its porosity, that is 0.95, and its dimension, that is 250 by 150 by 10 mm. So this is the top view of that one. So air flows from bottom. So whatever, because of this introduction of metal foam, the heat transfer surface area that will increases. So by that heat transfer enhances. So at the same time, as there is an obstruction to the fluid flow. So in the beginning case, empty case, there were no metal foams. So in that case, there was no obstruction. So the pumping power requirement, it was less. But now when we introduce metal foam, definitely there will be obstruction to the fluid flow. So pumping power requirement, it has to be enhanced. So pressure drop, it will be enhanced. So in order to measure the pressure drops, so pressure here, they have a pressure measuring devices, pressure taps there. So across the metal foam, they have placed it. So I too in the numerical simulation, at this location, I have measured the pressures. So pressure will increase. So we need to optimize this increased pressure of such a way that it should not, exceed the heat transfer performance. So that was my work. So in their work, what they have considered is the completely filled metal foam. So whatever the channel it is there, 27 mm, in that 1 mm it is heated. This is 3 mm, 3 mm, so 7 mm. So that means this one is 10 mm, this one is 10 mm. So for 10 mm, they have filled the metal foam. So in my case, what I have done is, I have considered partial filling cases. So I have taken 25% filling case. So figure A represent 25% filling, figure B represent 50% filling, and C 75% filling, and D as 100% filling. So what is the effect of partial filling over the completely filled channel? That analysis also I have performed. So this is the, as you can see it in this model. So the geometry, it is symmetrical along y-axis. So in order to reduce this computational time as well as the space that is required to store this one, so I have considered only half of the geometry. So that includes heater, one aluminum plate, and one metal foam it is there. So in that, the side wall we consider it as adiabatic wall conditions. Then air is traveling from bottom. So this is the inlet condition. So uniform velocity we have maintained. Then at the outlet, we have considered atmospheric pressure or gauge pressure as 0. Then this is the heater. So uniform heat flux is provided. This is the aluminum plate, and this is the metal foam we have filled it, and this we consider it as a symmetry. So here the simulation is performed by varying the velocities, different velocities like 0.1, 0.5, 1, like that we have varied the velocities. So for different cases also same boundary conditions what we have considered and we have performed. So in that it is observed that 100% filling, it gives more heat transfer. So if you use completely filled channels, yes, because of more surface area, so more heat has been transferred. But at the same time, pressure drop also it is more in case of 100% filling rate. So if you just concentrating only on the heat transfer performance, yes, 100% is the best option. But we need to consider the pressure drop also. So with the consideration of both heat transfer enhancement as well as this pressure drop, so we come to know that 75% filling gives a better result. So that is giving a good efficiency. So this is what our results it is focused. So that is one part of my work. So in the another part, once again I have considered one more experimental setup that is done by Borag et al. So the previous one is the vertical channel. Now it is the horizontal channel. So this is the test section. So there, this is a circular form. So okay, so this is the test section. It is, we can see it here. So inside that they have attached a metal foam to that pipe. Okay, so this is the entrance length and this is the exit length. So in order to validate that one, so I have also considered the same numerical model. So this is the test section. So this is 1000 mm length, 7 mm wall thickness, 100 mm diameter. So this is the metal foam that is attached to the inner wall of the pipe. So aluminum metal foam of 10 ppi and 0.95 same I have considered. So this is my numerical model. So this is the entry length, this is the exit length. So this is our test section. So they are also wounded a heater on the circumference of the pipe. So I have, in my work also I have supplied the heat, uniform heat I have provided, and they have considered completely filled. So I have to check completely filled as well as partial filling cases. So what you have presented here, one is partial filling cases. So here inlet velocity assumed to be uniform, then the outlet pressure, that is gauge pressure, we have considered it as 0, atmospheric pressure what we have maintained. So same conditions what we have considered with respect to previous one. That is one case. Then this in the another case. So in the previous case, this what we are seeing in figure A. So the metal foam, it is attached to the inner wall of the pipe. So now to check its best position, where it's going to give best thermodynamic performance. So what I have done is, so in first case I have attached the metal foam to the inner wall of the pipe. In the next case, I have inserted the metal foam at the core of the pipe, center of the pipe. So then once again that simulation is carried out. Then I have checked the performance. So from the performance it is, we come to know that, so the metal foam filling adjacent to the inner wall gives better performance compared to that of the metal foam insert at the core of the channel. The reason is that, so here from the, on the outer surfaces we are providing the heat. So as a result, so the metal foam wall that absorbs more heat and it will be transferred to the fluid. So more heat will be transferred there. At the same time, when the fluid is flowing at the, for these cases, when the fluid is flowing, so you know that the velocity it will be higher at the center of the pipe. So when there is high velocity, more obstruction, so pressure drop will increase. So for our better performance, pressure drop should be low, heat transfer should be high. So in these cases, so pressure drop is, heat transfer is high as well as pressure drop is low. So because of that factor, we are getting a good result for first cases. In that I have also very different thicknesses, like 10 mm thickness like this one, 10 mm, 20 mm thicknesses, 40, 60 and 80 mm. So I came to conclusion that by observing the result up to 40 mm thickness, it gives a good results. Okay, so that gives a good thermodynamic performance. So that is what my research work, and where we can use these metal foams. So we can use it for several applications in engineering disciplines. So in aerospace engineering, so like in cryogenic coolers, then in electronic equipments like your CPUs, GPUs, okay, battery coolers, then in solar systems, even in medical field, MRI scanners, okay, to enhance the cooling rate, as well as in especially it is more focused on compact heat exchangers. So because the property of metal foam one is that it is having high surface to volume ratio, so it is more suitable to use it in compact heat exchangers. So radiators, so refrigerators, air conditioners, so there we can make use of it. And also we can use it in geothermal systems. So for filtration purpose also we can make use of it. Then also for solidification purpose, in order to enhance the cooling rate, so we can make use of for all these things, as well as we can use it in the combustion chamber. So if you use it in combustion chamber, what is the advantages that we are going to get it? So this is not my work, so just in link to this course, so just I have to consider this factor. So of course, if you use this metal foam, the primary objective of using the metal foam is to enhance heat transfer performance. So of course, when you introduce this metal foam in the channel combustion chamber, definitely heat transfer will enhances. So another factor, what is that? It gives flame stabilization. So that means, as you have seen this shape of this metal foam, it is having intricate shape. So when the fluid it is flowing through that one, it will create turbulence flow. It is not a laminar flow. So it will create a turbulence flow. As a result, the proper mixture of fuel and air takes places. So because of that proper mixing, so combustion, it will take places completely, almost it is completely. So the left out unburnt gases, it will be very less. So we can reduce that one. So if the unburnt gases, if it is left out is less, that indicates that, so the emission of pollutants like NOx, nitrogen oxide or nitrogen dioxide, like carbon monoxide, so that emission can be reduced. So that is the advantage of using metal foam. Then, as I told you, it can also be used for some specific purposes like a insulator. So where we can absorb that heat and store it, so it should not be lost the heat. So there also we can use it, and it is having a good energy absorber capacity. So for noise as well as damping coefficient, so that can vibration, it can withstand and it can reliable. So for long many days, and it is a lightweight component, metal foam. So fuel efficiency, it will be a factor. So we can increase the fuel efficiency. So because of that, we can use it in aerospace applications and automotive applications. So this is the one factor. And use of this metal foam in combustion process, so we can control the combustion rates. So that is as I have shown, this pore density or porosity. Okay, so we can manufacture according to our requirement, like 10 ppi, 20 ppi, 45 ppi, like that. According to our requirement, we can manufacture and we can control the propagation of flames. So all these options that is available if you use this metal foam in a combustion process. So this is regarding my presentation. So these are the references, and these are the, with respect to my research work, these are the publications that I have done. So all are SCI journals, so and book chapters, then conferences where I have presented, and for the second paper I have received a best paper presentation award. So this is regarding the presentations. Any questions if you have?
Thank you.
Thank you.
I have a question.
Yeah.
Can you please specify which metal alloy has been used?
Aluminium metal. So generally metal foam is created by using different materials like aluminium, copper, zinc, titanium, all those things. So as you are aware of it, copper is a good conductor of heat. Okay, so that is also in the literature I have observed it. Copper is a good conductor, and also aluminium also in some researchers they have used. So what I came to know that, so yes, of course copper gives good result, but it is not much compared with respect to aluminium. So it is somewhat slightly improvement it is there, but yes, of course it is a numerical study, we can use it, but when it comes to practicality, cost will be higher. We need to consider that factor also. So considering that cost factor as well as that performance, so aluminium plays a good option for me. So that's why I used aluminium.
Okay. Also in slide number 15, you mentioned that that it is also good for noise and vibration damping.
Yeah.
My question is, some materials, especially metal foams, when they absorb noise and vibration and they damp, they are basically absorbing energy, and they mitigate it by managing by heat transfer as well. But in the process, they also get somewhat heated.
Yeah.
So I think that if their temperature rises, it would affect their heat transfer negatively. So heat transfer rate would decrease somehow.
See, this is metal foam. It also acts like a catalyst. So that is also one thing. So whatever that vibration damping that can be converted into heat form also.
Yeah, that's what
Ah.
I'm saying. If it's getting converted into heat form and staying in as heat energy in the ligaments of the porous material, so that would affect the heat transfer rate, right? If the temperature
That's only, it's going to increase the heat transfer performance only.
No, I'm saying that it would decrease because the temperature difference would reduce. As the temperature of the metal foam, that would go up. So the temperature difference would be reduced, so the heat transfer rate would also reduce, is what I'm trying to say.
So there will be a gases, so in combustion, so that will carry out that whatever the heat will be there in the metal form, that will be carried out by the few gases.
This question, it is true that if you use that foam for a longer run,
Yes, sir.
Longer
that
run.
effect, that is a question I believe,
Yeah.
isn't it?
Yes, sir.
How to see, there are a lot of emissions with particles that comes up. So one point of time you saying that it will allow the heat transfer. But with time, if the same material getting used, they will act as a kind of a insulation for because of other particles that gets developed through this process of its use.
Yes. So this is I need to work on, sir. So this is my research work was previous one. So whatever I've shown. So this is just to relate to this course, So I have considered this topic, how my metal foam can be utilized in combustion chambers also, process also. So that we need to work on.
My thing is that you have to think about whatever foam material, you have to do some kind of life cycle analysis.
Yeah.
Okay. You can say that you use it for this melting vessel, so to have good effect in transfer. That may be possible to study.
Yes, we can concentrate on that. Thank you.
Can you show your material parameters at the beginning? I think it was slide number 2 again. No, then it was where you have said you have a mean diameter which you can.
Yeah, so
maybe
this one.
but later do one here.
So there, so usually that pores, it is not exactly circular. Okay, so it is somewhat oval in shape. It will be like that. So average diameter. So the diameter, whatever they have measured. So in the as I've taken the study, means these parameters I have taken from Kamath et al. So their experimental study. So they have
from whom?
Kamath et al. So that is experimental done in IIT Madras.
Right.
So this is the.
Yeah, that's okay. That's the final question. So, who is measuring these qualities? So you are not.
They have done all these parameters, sir. So they are experimentally done that work.
Yeah.
So for my research work, so their work, what they have shown is that if you introduce metal foam, it enhances heat transfer. So that is what they have presented. So my work, I have considered the same parameters and I have simulated. And what is my work is that, so yes, of course it increases heat transfer. So up to what limit we can use it?
So you have said you have a mean diameter.
Yeah, that is what.
This is not sufficient. You also need the standard deviation.
They have used the standard procedures and all those things, sir.
Yeah, but so if you don't measure it, so do you get these data? So the standard deviation also from the other group?
Yeah, that is one microscope, it is there. So the standard microscope, so that name I have forgotten. So using that microscope, they are going to measure it.
So you have a mean value and
you
also get a standard deviation.
Yes, there is a deviations also there. So they have presented all these parameters. So that's why, so when we validated our results with the experimental results, some deviations we are going to get it because of these parameters.
Yeah.
So
then I think it's one of the next slides where you discuss the heat transfer. Maybe one further. Yeah, here.
Yeah.
So in which dimension you are interested concerning the heat transfer? Is it the heating of the gas flow going from the
Air,
bottom
the
to the
fluid,
top,
we are
or the heat transfer from the hot wire in the metal?
This is the heater, sir. So,
Yeah.
from the heater, the heat will be transferred to the aluminum plates.
Yeah.
So, aluminum plates get heated up. So, that is our metal solid surface. Okay. So, we are passing air from the bottom.
Yeah.
Okay. So, that air, when it comes in contact with the surfaces by convection phenomena, the heat will be carried away by
The
the.
question is, which quantity is here of interest for you? The
Yes,
transfer to
the
gas
heat
flow?
transferred, that is heat carried away by the air. So, that is what more interest. So, if more heat is transferred, so that is good performance. If the less heat, the air, if it carries less heat, that means heat transfer is lesser. So, our focus is on that one.
So you have as a flow resistance on the one hand, which
Yes,
you have
flow
to
resistance.
optimize, and you have to optimize the heat transfer to the gas phase. Then finally, concerning your burner, is it a mild combustion process? That means is the flame inside the porous structure, or is the porous structure used to laminarize the flow, and the flame is above the porous structure?
Regarding that combustion, linking to that I need to work on, sir. So, that I do not have proper information regarding that. So, that I need to work on. So, this was my research work. So, when it comes to this combustion chamber, as one case, I think we can insert inside the combustion chamber also. So, in one figure that I have shown it. So, here outside this also we can like this. We can insert.
Yeah, but then it's heat transport away from the combustion zone, so for cooling.
Yeah.
Yeah. Okay. So
That is also one cases that is
okay,
possible.
I thought so you can use these structures either in laminar flame burners, as in so the gas flows from
the
bottom
bottom
to
to
top,
top.
and at the top you have a very laminarized flow, and you have the flame above the structure. But we also have mild combustion processes where the flame is inside the porous structure.
Inside, okay.
But okay, you have a totally different application. Yeah, thank you.
Yes, thank you.
Question?
So just go to the computational model. So you have done the 2D analysis.
Yeah. 2-dimensional we have considered. So, Gambit was the software that I have used, and for simulation purpose, ANSYS Fluent. What I have used.
No, means what my concern is that is related to Detlev also. So when you are just stacking the pole, so the poles are aligned in one direction.
Yeah.
So if you are taking a cross section and if you are putting it, so that velocity in the cross sectional way, if you will think it, in one way the pole will support the flow, in the other way it will restrict the flow. So in which way you have to simulate it? So that is what my concern.
So, I didn't get your question.
So did I get my question on it? So just to go to that metal foam picture. Yeah.
Yeah.
You will see it. So it will blow from the bottom. So the holes will support the flow.
That will allow the fluid to flow. Yeah.
Okay. So you will see it in the crosswise from the sideways towards the board. So it will restrict the flow.
Yeah, that will be there.
Okay.
So, when there is no metal foam, fluid will easily flow. So, in that cases, okay, so the heat transfer enhancement will be lesser. So, when we introduce this metal foam, so this will, so we can see it here. Yeah. So, in the first case, if there is no metal foam, just air comes from the bottom and carries the heat from the aluminum plate. Okay. So, when we introduce this metal foam, the whatever the heat that was there in the aluminum plate, that will also transfer to the metal foam. So, that ligaments, whatever I have said, so from that the metal surface area increases. So here it will comes in interaction with that ligaments, and it will carries more heat. So if there is no metal foam, so the pumping power requirement, the resistance will be less. So
you have kept the both sides same.
Means when we manufacture, that depends upon the preparation of that metal foam.
Leave that one.
Yeah.
So for the simulation, you have kept the both sides same for everywhere.
Yeah. So porosity, what I have told, 10 ppi. So 10 means pore density we can calculate as 10 ppi, and porosity that we kept constant.
Another point is that whenever you will simulate it with smaller diameter or the larger diameter ones, so the attachment with the heater, so the surface area that is getting attached to the heater, that will vary.
Yeah.
So the conduction of heat towards that foam, so that will vary.
Yeah, definitely. That is what I told you. So the factors of pore density, porosity plays a major role in the heat transfer enhancement. So that by varying that one also, we can do the investigation and all those things.
My question is that, so when you are keeping it at a 25%, 50% and
Yeah.
70% one, so along with that, how this conduction part is being affected? So have you tested anyway?
Conduction part.
Means the transfer of heat from the
Yeah,
heater
yeah.
toward the
That is conduction. So it is a combination of both conduction as well as convection that is taking places. Yes.
So here, if you are changing the pore size, so the conduction part will be more.
Yeah.
If you are reducing the amount of
Metal foam. Yeah, filling
so
percent.
the convection part will be more.
Yeah.
Okay. So there might be some coordination in between these two. Means how much portion should be attached with the heater and how much flow should be there from the bottom.
See, in all the cases, the contact with this aluminum metal foam, that is same for all the cases.
Yeah, here I am doing. I am not talking about the present.
Yeah. That is fine.
He is saying that you can extend this analysis.
Yeah. That is what
So
we
that
can.
conduction and
Convection.
can be coordinated.
Yes.
To find an optimum pore size.
And here you are using air.
Yes. We can use it. Miss.
So if you think it in terms of heat exchange of pores, then that water or
Yes,
oil,
that can also be done. So that
if
further
there are
analysis we
chemicals
can.
are available with that.
Yeah, available. So we can use water also, as well as I told you nanofluids.
Okay.
So basic water plus along with like cuprous oxide or copper oxide, aluminum oxide, iron oxide, like that nanofluid can also be introduced. So further enhancement it is possible.
You have a plot of your grid you have used?
Yes, sir. I have considered that grid study also. Grid study.
So the
No,
numerical
in this
grid,
presentation I have not presented.
question is, how do you resolve this porous structure? So you use Gambit for
Gambit, yes.
grid generator, and then you use Fluent or
Gambit, it is for machine modeling and machine purposes. I have used Gambit, and for simulation purpose I have used ANSYS Fluent. ANSYS Fluent.
and the Fluent. Yeah, so you solve the equation system for the gas phase. So how do you resolve this porous structure? Is it just an solid block with specific parameters, or do you have a fine grid and you have all the fine channels?
Solid it is there, sir. Then grid.
So when you look at Fluent, you can represent porous structures by some specific parameters. Let's say in this area I have a porous structure with this porosity, this density, this heat transfer coefficient, and so on. So you do not resolve it very fine, because you're not interested what is happening inside the porous structure.
That flow is also very much important parameters, flow through porous structure. So in that also we have considered laminar, transition and turbulent regions.
Do you resolve this?
Yeah.
So
So
your grid also, you have a very fine mesh inside your grid which represents the material.
yes, sir. Yes, sir.
Yeah.
So we have considered that factor also. So based on the pore diameter, we have calculated the Reynolds number. So for empty channel, so as we know it, less than 2300 laminar flow transition between 2300 to 4000 and above that turbulent. So same way for porous media also. So we have calculated the Reynolds number based on the pore diameter. So in the literature it was observed that if it is less than 150, then the laminar flow it will be considered there. So if it is greater than that, turbulent flow it will be considered. So based on our cases, so we have considered
the question I have, if you have different possibilities to use, for example, flow and for this. So your grid is here and here. Here you solve your equation system, and this is represented just by 1, 2, 3 numbers, and you have here a boundary and here a boundary. So you say the flow is coming here with a velocity of blah blah blah. Can you go back up? And a temperature of Kelvin, and then you continue calculation here, and this path here is just represented by some parameters. Or you can resolve this also in your grid, so you have also some elements where you solve your equation system. That was my question. How are you doing this?
Yes, we have some governing equations. So
you do not resolve this?
I have not resolved that one. So
yeah,
that the Fluent software it is there, no? So that it takes care of that one. So we have that continuity equations, momentum equations, energy equations that will be there. So that parameters.
No. Do you have grid points here inside?
No.
It's just represented a simple model.
Yeah.
That was my question.
Yeah.
Thank you.
To measure this temperature and all those things, we have thermocapacities attached here.
How this study is different from porous radiant burner? Porous radiant burner you have heard of? We have some radiant burners, not conventional gas burners we have, where the mode of heat transfer is mainly convection. Radiant burner is only, mode of heat transfer is only radiation. So conventional burner can be modified with a porous structure. So it is claimed that their efficiency can be enhanced.
Yes, we have to look into that.
There also porosity plays a very important role.
Yeah.
And in porous burner case, the materials are different. Ceramics.
Yeah.
Yeah, that is what exactly my question is. Because in the porous radiant burner, the flame moves through the holes. Okay. So here also the air should move through the holes.
Yeah.
But here as per the structure, so it's not moving through the holes. As it is a two-dimensional analysis, that is why the restrictions are more. Air is not flowing through it. Okay. Otherwise, if it could have been a 3D analysis, then the structures are not opposed much. Okay, so it might have allowed the air to flow through those structures, through the holes. But here it is indicating that the boundaries are opposing the flow.
No, it's just a representation of that one.
His research was something on heat transfer. He has not probably.
This is there is no boundary like that. So it's just a representation.
So you are, I know you are defending
what he is asking. Like let's say you should stack this foam, metal foam.
Yeah.
You stack it up. If the holes are not aligned properly in experimental application.
Yes, definitely.
If they are not aligned properly, then of course they flow and there will be more pressure.
Yeah, that is what. When we introduce the metal foam, pressure drop definitely increases.
If you could have given any streamline flow here, then it could have been more clear whether the fluid is entering into that honeycomb structure or not.
Yes, it will enter. See, this is just a representation. I have a boundary like this.
Yes.
So actually, it is like if it is a metal foam, air will flow through this one.
That is the main.
Yeah, it will flow. So just a schematic representation, I have shown it.
No, it is flowing.
Yeah, it is flowing through this one.
Simulation, you have not made grid, na?
it's not necessary for you can represent it by specific parameters you have measured or you get from the other group.
Okay.
Okay, you have to think about the extension of this work in the frame of combustions, radiant burners, that becomes more effective. Second thing what he says is that ceramic materials can be distinct. Anyway, you are here for 2 years, so you can make some proposal in this line.
Sure.
Maybe during your 2 years you can think about doing some research on this line.
Yeah. Thank you.
So anyway, this presentation helps you to write a proposal. You have been asking what are the topics I will do. One topic you can think of this.
Yes. Yes. Thank you.
Any discussion? One thing, and they will be giving some sheets like this. You receive it. Don't submit now. Towards the value just before a day of validatory session, you submit all the sheets together. One student, all five. One participant, all five. And write your name, roll number, not your name and set name. Okay. One time sufficient for them, comparison will be easy. For us, recording, keeping of office records. Okay, we will close for this session. Thank you. चाय वगैरह लाया क्या? दे दो लेके जाओ. लाया? लेक्चर करिए हमर मैंडेटरी रिक्वायरमेंट करते हिसाब करिए हम आपके